Have you ever looked up at the night sky and wondered if we are truly alone in this vast universe? What if I told you that the cosmos might be sending us messages, not in any language we understand, but through mysterious, powerful bursts of energy that appear and vanish in the blink of an eye? These are unexplained galactic signals, some of the most baffling and thrilling phenomena ever detected by humanity. They emerge from the deepest, darkest corners of space, carrying with them secrets that challenge everything we think we know about the universe. Imagine for a moment a signal so intense that it outshines entire galaxies, yet lasts only a fraction of a second. These aren't science fiction, they're real, they're happening right now, and they've left scientists both mesmerized and mystified. Each one is like a cosmic fingerprint, unique and puzzling, hinting at origins that range from collapsing stars to, dare we say, something beyond our current comprehension. The very idea sends shivers down the spine. Could these be natural cosmic events, or is there a possibility, however remote, that they are evidence of intelligence far greater than our own? In this video, we're embarking on a journey to explore 30 of these extraordinary signals, each with its own story and its own set of incredible theories. From swirling neutron stars to speculative technologies of advanced civilizations, we'll dive into the most compelling explanations that astronomers and researchers have proposed. This isn't just about facts and data, it's about the human spirit of curiosity, the relentless pursuit of understanding, and the awe-inspiring possibility that we are on the verge of discoveries that could redefine our place in the cosmos. So settle in, open your mind, and get ready to join the greatest detective story ever told, the one written in the stars. Of all the signals that have ever reached Earth from the depths of space, none has captured our collective imagination quite like the one known simply as the WOW signal. This wasn't just data on a chart, it was a moment of such profound shock and excitement for one astronomer that he scrawled a single, emphatic word of pure disbelief right on the readout, giving this cosmic mystery its unforgettable name. It was the evening of August 15, 1977, at Ohio State University's Big Ear radio telescope. The telescope was performing its silent, methodical scan of the heavens, part of the ongoing search for extraterrestrial intelligence, or SETI program, listening for any whisper that seemed out of the ordinary. And on that night, it heard a shout. For exactly 72 seconds, the Big Ear telescope locked onto a signal so powerful and so peculiar that it defied all conventional explanation. It wasn't the messy, broad static of a natural cosmic event. This was a pristine, narrowband radio signal, blazing at exactly 1420 megahertz. Now, that frequency is not a random number, it's profoundly significant in astronomy. It's the resonant frequency emitted by neutral hydrogen, the most abundant element in the universe. The reasoning among scientists was that any intelligent civilization attempting to announce its presence would logically use this universal landmark, a sort of galactic hailing frequency, because it's a wavelength any listening civilization would understand as fundamental. The signal's intensity rose and then fell over that 72-second window in a perfect curve, precisely matching what you would expect as the telescope's fixed receiver slowly drifted across a stationary point source in the sky. It was a perfect textbook signal. The astronomer who discovered it days later, Jerry Amon, circled the alphanumeric code 6EQUJ5 on the continuous printout and in the margin wrote that now iconic word, WOW. His reaction was born from the data itself. The signal's strength was off the charts, represented by the value 6 on a scale that only went up to 9. And the alphanumeric sequence used a system where a value of U was actually stronger than what the system was technically designed to measure. It was, by every metric, an anomaly of staggering intensity. The immediate and obvious question was, what could possibly generate such a powerful, focused, and seemingly artificial signal? The hunt for an answer began immediately. The most tantalizing possibility, of course, was that we had finally heard a sign of intelligent life, but science requires verification. So astronomers pointed every available instrument they could back at that exact spot in the constellation Sagittarius, listening for a repeat performance. They listened again and again for months, then years, and eventually for decades, but the signal never returned, not once. It was a one-time event, a single, brilliant shout into the void that was gone as suddenly as it appeared. This enduring silence is what fuels the mystery and has led to a long list of proposed natural explanations, though each has its own flaws. Could it have been a reflection of a human-made satellite signal bouncing off a piece of space debris? The specific frequency of 1420 MHz is internationally protected for astronomical research, making terrestrial transmission highly illegal and unlikely. Perhaps it was an undiscovered cometary phenomenon. Some researchers have proposed this, but the timing doesn't align with known comets in the region. The most likely natural explanation is that it was some extremely rare and short-lived astrophysical event that we simply don't yet understand. But the possibility, however faint, that Jerry Amon's "wow" was a genuine response to our own silent gazing out into the cosmos remains one of the most powerful and haunting what-ifs in the history of science. It stands as a ghost, a single data point that refuses to be forgotten, reminding us that the universe is still full of voices we have yet to understand. Yet for all the tantalizing mystery of a single, silent event like the "wow" signal, the cosmos had an even bigger surprise in store, one that would completely reshape the scientific search for answers. We now turn to an entire class of cosmic enigmas known as fast radio bursts, or FRB. These are not mere whispers from the void. They are the universe's most powerful and shortest-lived explosions of radio energy. Imagine a flash of radio light so intense that it can outshine 500 million suns, yet it originates from a source billions of light years away and lasts for just a few thousandths of a second. When the first one was discovered in 2007, it was so bizarre and so brief that many astronomers dismissed it as a one-time glitch, perhaps an earthly instrument error. But as more were found, a pattern of cosmic violence emerged. The leading theory was that each FRB was the final, dying scream of a catastrophic event, a neutron star collapsing into a black hole, or two incredibly dense stellar corpses smashing together in a merger that vaporizes them both. These were thought to be universe-altering explosions that could only happen once. That is, until we found one that refused to die. This brings us to the signal that truly broke the mold and sent astronomers back to the drawing board, FRB 1200-1102. Discovered in 2012 and confirmed as a repeater in 2016, this single object shattered the cataclysm theory into a million pieces. Here was a source out in the depths of space that was firing off these incredibly powerful bursts not just once, but over and over again, and its pattern was utterly chaotic. It would sometimes remain silent for weeks, then suddenly erupt in a frantic storm of dozens of bursts in under an hour. There was no rhythm, no predictable schedule. It was as erratic and untamable as a volcanic eruption. This single discovery forced a monumental shift in our thinking. If this FRB could repeat, then its source couldn't be destroyed in the process. It had to be surviving the event, meaning the engine behind these bursts had to be something that could power them repeatedly. The plot thickened even further when astronomers managed to pinpoint its cosmic address. FRB 1200-1102 wasn't just anywhere. It was located in a tiny, faint dwarf galaxy, a staggering 3 billion light-years from Earth. This specific environment is a crucial clue. Dwarf galaxies are often considered cosmic fossils, ancient and relatively pristine environments that lack the heavy elements common in larger galaxies like our own Milky Way. They are the perfect nurseries for certain types of exotic, long-dead stars. This location immediately ruled out many proposed explanations that were tied to more evolved stellar neighborhoods. The fact that it repeats completely opened the floodgates for entirely new avenues of study and theorizing. For the first time, astronomers could point the world's most powerful telescopes at a known FRB location and wait, knowing that another burst was not just possible but probable. This allowed for unprecedented observation and led to another bombshell discovery. The bursts from FRB 1200-1102 were highly polarized, meaning their radio waves were twisted. This twisting, known as Faraday rotation, indicated that the bursts had traveled through an incredibly powerful magnetic field, suggesting the source is surrounded by a vast, turbulent nebula of magnetized plasma. The most compelling theory that fits all these clues points to a magnetar, a specific type of neutron star with the most powerful magnetic fields in the universe, as the likely culprit. Perhaps this magnetar is a young, hyperactive stellar remnant, and these bursts are massive starquakes on its surface or eruptions from its tumultuous magnetosphere. But even this solid theory has its challenges, and the door remains open for more exotic ideas, including the possibility of a powerful alien transmitter, because the repetition shows a clear and undeniable intelligence behind the phenomenon, though that intelligence is almost certainly the natural, yet still poorly understood, physics of an extreme universe. Just when the scientific community thought fast radio bursts couldn't get any stranger, along came one that didn't just repeat randomly, it kept a schedule. While FRB 1200-1102 was a chaotic rebel, its cousin, FRB 1891-6, emerged as a cosmic timekeeper, introducing a rhythm to the randomness that was both astonishing and deeply revealing. Discovered by the CHIME telescope in Canada, this signal originates not in a distant dwarf galaxy, but from a much closer and surprisingly familiar environment, a spiral galaxy much like our own Milky Way, located a comparatively nearby 500 million light-years away. Its proximity made it far easier to study in fine detail, and what those detailed observations uncovered was nothing short of a paradigm shift. This FRB operates on a precise 16.35-day cycle, a clockwork pattern that is utterly unprecedented in the study of these cosmic flashes. For roughly 4 days, it enters an active phase, firing off multiple bursts in a seemingly frantic period of productivity. Then, as if a switch is flipped, it falls completely silent for the next 12 days. This isn't a suggestion of a pattern. It's a definitive, predictable loop of activity and quiescence that has been observed over and over again. The existence of such a clear periodicity is a monumental clue. It strongly suggests that whatever is producing these titanic bursts of energy is not being destroyed. It is part of a stable, ongoing system whose mechanics are governed by a regular orbital or rotational cycle. This regularity immediately narrows down the list of possible culprits from a vast field of maybes to a few highly compelling theories. The leading explanation points to a neutron star, specifically one with a wobble. Imagine a rapidly spinning neutron star, its beam of radiation sweeping through space like a lighthouse. If this neutron star is also precessing, meaning its rotational axis is itself slowly wobbling in a circle over time, much like a spinning top about to fall over, that lighthouse beam would only point toward Earth during a specific part of that wobble cycle. The 16-day period could perfectly represent the time it takes for one complete wobble, with the 4-day active window being the precise moment its deadly beam crosses our line of sight. This would make the FRB a natural, albeit extreme, astrophysical phenomenon. Another powerful theory involves a binary dance of death. Picture a highly elliptical orbit where a neutron star, or perhaps a magnetar, is locked in a gravitational embrace with a massive companion star. As the neutron star travels along its stretched, oval-shaped path, it would only venture close enough to its companion to interact violently during a brief periastron passage. This close encounter could trigger immense eruptions on the neutron star's surface or cause it to plow through the dense stellar wind of its partner, generating the intense radio bursts we see. The 16-day cycle would simply be its orbital period, with the active window corresponding to its dangerous and dramatic close approach. This model turns the FRB from a solitary actor into one half of a dynamic, destructive partnership. The discovery of this rhythmic repeater is arguably one of the most important breakthroughs in the entire field. It provides a predictable natural laboratory, allowing astronomers to point their telescopes at the exact right time with a high degree of confidence that they will capture a burst in action. This has enabled incredibly detailed studies of the signal's properties and its local environment, offering glimpses into the structure of the magnetic fields and the density of material surrounding the source. FRB 1891-6 demonstrates that these mysterious engines are not just one-off catastrophes, but can be long-lived objects following the fundamental laws of orbital and rotational mechanics. It tells us that the key to unlocking the FRB mystery may not be found in searching for more randomness, but in listening for the subtle, hidden rhythms of the cosmos. While the rhythmic beat of FRB 1891-6 gave us a pattern to study, the entire field of fast radio bursts owes its existence to a single, monumental discovery, one that was found not in real time, but by looking back through the archives, a cosmic ghost hiding in plain sight. This is the story of the Lorimer burst, officially known as FRB 010724, the event that started it all. It was 2007, and astronomer Duncan Lorimer and his student were sifting through old data from the Parkes Radio Telescope in Australia, recorded 6 years earlier in July 2001. They weren't hunting for something new, they were performing a routine review of observations meant to study pulsars. But buried in that mountain of data was an anomaly so extreme it would have been easy to dismiss as nonsense. It was a single burst of radio waves, a spike on the readout that lasted a mere 5 milliseconds. But in that 5,000th of a second, it released more energy than our sun puts out over 300,000 years. The sheer power was staggering, but the real clue to its origin was something called the dispersion measure. As radio waves travel across the vast, almost empty space between galaxies, they interact with the sparse sea of free electrons, an invisible fog that slows them down. Higher frequency waves travel through this fog a tiny bit faster than lower frequency waves. This means a signal that starts out as a sharp, simultaneous blast of all frequencies gets smeared out by the time it reaches us. The lower frequencies arrive noticeably later than the higher ones. The amount of this delay is the dispersion measure, and it acts as a cosmic odometer. The greater the delay, the more electrons the signal has traveled through, and therefore the greater the distance it has come from. The dispersion measure for the Lorimer burst was enormous. It pointed unequivocally to an origin far, far beyond our own Milky Way galaxy, placing its source billions of light years away in the deep extragalactic void. This conclusion, however, was met with intense skepticism and even outright dismissal from much of the astronomical community. The idea of a solitary, millisecond burst of energy powerful enough to be seen from another galaxy was so preposterous that it challenged the very foundations of astrophysics. What known natural process could possibly be that violent, that brief, and that energetic? The immediate and logical assumption was that it had to be a local glitch. Critics proposed it was terrestrial interference, perhaps a microwave oven being opened prematurely by an impatient researcher at the observatory, or a cell phone signal bouncing off a passing airplane. Others argued it was an instrumental artifact, a one-in-a-million electronic hiccup within the telescope's own complex machinery. For years, the Lorimer burst was treated as a fascinating but ultimately flawed data point, an unexplained curiosity that was probably just human error. But Duncan Lorimer and a small group of supporters held their ground. They meticulously ruled out every possible terrestrial explanation they could conceive of. The signal's characteristics, its specific frequency sweep, and its position in the sky didn't match any known human-made source or common instrumental failure. They argued that they had found something genuinely new, a previously unobserved class of astrophysical phenomenon. It was a lonely position to hold. The scientific process, by its nature, is conservative. Extraordinary claims require extraordinary evidence, and a single, unrepeatable event is the antithesis of verifiable evidence. For half a decade, the Lorimer burst remained an unresolved puzzle, a tantalizing but unproven clue. Its ultimate validation did not come from debate but from discovery. The turning point arrived when other astronomers began to find more of them. A second one was discovered, then a third, each with that same incredible dispersion measure pointing to extragalactic distances. With each new detection, the argument that these were all mere glitches became statistically impossible. The Lorimer burst was retroactively crowned as the first of its kind, the progenitor. It was no longer an anomaly, it was an archetype. This single 5-millisecond event discovered in forgotten data ignited an entirely new and vibrant field of astronomy. It forced scientists to confront the reality that the universe is capable of generating unimaginably powerful, transient explosions that we had been completely blind to. It taught us a humbling lesson that sometimes the most universe-shattering discoveries aren't made by looking out at the stars, but by looking back through our own data with fresh, curious, and stubbornly determined eyes. While the powerful, extragalactic blasts of fast radio bursts capture headlines for their sheer cosmic violence, the search for signs of intelligent life often focuses on something far more subtle and deliberate, a persistent, narrow signal that seems to whisper rather than shout. This brings us to one of the most intriguing and hotly debated candidates in the history of SETI, a signal known as SHB-02+14a, unlike the WOW signal, which was a one-off event. This anomaly was detected not once, but 3 separate times in 2003, and it wasn't found by a massive, solitary radio telescope. It was discovered by millions of us through our personal home computers. This was the flagship discovery of the SETI at Home project, a groundbreaking distributed computing effort that allowed anyone with an internet connection to donate their computer's spare processing power to sift through the mountains of data from the Arecibo radio telescope, searching for that one in a billion needle in the cosmic haystack. SHB-02+14a was that needle. The signal appeared to originate from a point in the sky between the constellations Pisces and Aries, but its location wasn't the most compelling part, its properties were. First, its frequency was recorded at around 1420 MHz, hovering remarkably close to the hydrogen line. This is the universal watermark, the frequency that scientists have long theorized any advanced civilization might use for intentional interstellar communication because of its fundamental significance across the cosmos. The second, and perhaps even more tantalizing, characteristic was its drift rate. A radio signal transmitted from a planet that is rotating and orbiting a star will appear to change frequency slightly from our perspective on Earth due to the Doppler effect, the same phenomenon that makes a siren's pitch change as an ambulance speeds past you. This change in frequency is measured as a drift rate. The drift rate of SHB-02+14a was measured, with significant uncertainty, to be between -0.08 and -0.16 Hz per second. Some researchers argued that this value could be consistent with a transmitter placed on a planet with a rotation period similar to Earth's, orbiting a star at a distance that would place it within its habitable zone, the so-called Goldilocks region where conditions might be just right for liquid water, and therefore life as we know it to exist. For a brief, thrilling moment, it seemed like the SETI at Home project might have actually found what it was looking for, a persistent, intelligent beacon from a world not entirely unlike our own. The idea captured the public's imagination because it was a discovery made by the people for the people. It felt like a modern-day version of the story behind the WOW signal, but with the power of global collaboration behind it. Yet, almost as quickly as the excitement built, a wave of significant skepticism and rigorous scientific scrutiny washed over the discovery. The signal was exceptionally weak, barely rising above the background noise. It was detected 3 times, but each detection was at a slightly different frequency, which is not what you would expect from a stable, purpose-built beacon. A deliberate transmitter from an advanced civilization would likely be far more powerful and locked onto a specific frequency with extreme precision. The most probable explanation, and the one widely accepted by the broader astronomical community, is that SHGB 02+14 was nothing more than an unfortunate and incredibly rare combination of random noise. The SETI-at-home data analysis involved breaking the telescope's wide-frequency recordings into billions of very narrow channels, looking for a persistent signal in one channel. The project's own scientists estimated that even by chance alone, a few signals would appear to detect multiple times purely through random statistical fluctuations in the background static of the universe. SHGB 02+14 is almost certainly one of those statistical ghosts. It was a fluctuation that, by pure luck, happened to align with some of the parameters we associate with an artificial signal, making it a classic example of what scientists call a false positive. Despite its ultimately disappointing explanation, the signal remains an important cultural and scientific touchstone. It demonstrated the incredible power of citizen science to engage the world in a grand cosmic quest, and it underscored the immense challenge of finding a genuine signal amid the endless roar of the universe. It taught us that the search itself is a process of patiently sifting through countless possibilities, knowing that most will be mirages, but that the next one could always be the real thing. Just as the story of SHGB 02+14 demonstrated the immense challenge of separating a true signal from the noise of random chance, our search for cosmic neighbors would soon face an even more tantalizing and frustrating test, one that emerged from the one place we might most expect to find life, right next door. In December of 2020, the astronomical community was set ablaze by a detection so compelling it seemed almost too good to be true. The Breakthrough Listen project, a monumental $100 million initiative dedicated to finding signs of intelligent life, was using the Parkes Marion radio telescope in Australia to observe our closest stellar neighbor, the Proxima Centauri system. This wasn't a random point in the sky, it's a system we know intimately. Proxima Centauri is a red dwarf star just 4.2 light-years away, and we know it hosts at least one rocky planet, Proxima Centauri b, nestled snugly within its habitable zone. To detect a potential technosignature from this specific location would be nothing short of historic, and for a few exhilarating hours it looked like they might have done it. The signal was designated BLC-1 for Breakthrough Listen Candidate 1. It was observed during a total of 30 hours of observations spread over several days, but it only appeared once for a duration of about 5 hours. What made it so instantly intriguing were its near-perfect characteristics. First, it was a narrowband signal. Natural cosmic objects like pulsars or merging black holes produce radio emissions that are broadband, spread out across a wide range of frequencies. BLC-1 was concentrated in a very specific, narrow slice of the radio spectrum, exactly the kind of signature we would expect from a focused, artificial transmitter. Second, it exhibited a drift rate. As we discussed, a signal from a planet will change frequency slightly due to the Doppler shift caused by its motion. The drift rate of BLC-1 was consistent with what you might expect from a transmitter located on a planet orbiting Proxima Centauri. It wasn't a static tone. It was a tone that was subtly sliding in frequency in a way that mimicked a transmitter on a moving world. The initial analysis was cautiously optimistic. The signal was found in data that had been specifically filtered to remove the vast majority of common, human-made radio frequency interference, or RFI. Our planet is drowning in a sea of our own radio noise from satellites, radar, cell phones, and even microwave ovens. The Breakthrough Listen team uses incredibly sophisticated algorithms to filter out these terrestrial signals, which typically have telltale signs like being present in the telescope's side lobes or appearing at fixed frequencies. BLC-1 had passed these initial filters, making it seem like a genuine candidate from beyond our world. The excitement was palpable. A signal from the nearest star with a habitable zone planet was the scenario every SETI scientist had dreamed of. But the true scientific process isn't about the initial excitement. It's about rigorous, relentless verification. The Breakthrough Listen team did not announce the discovery. Instead, they embarked on a painstaking, year-long analysis, subjecting the signal to every test they could conceive of. They went back and re-observed the Proxima Centauri system for another 60 hours with the Parkes telescope, listening intently for a repeat of the signal. They pointed other telescopes like the Green Bank Telescope in West Virginia at the same location. The silence was deafening. BLC-1 never returned. This was the first major red flag. A deliberate alien beacon designed for communication would likely be persistent or repeating, not a one-off event. The team then dove deeper into the signal's properties, and the cracks began to show. While the signal's drift rate was consistent with a transmitter at Proxima Centauri, it was also consistent with something far more mundane, an oscillator drifting due to a change in temperature. Many human electronic devices use crystal oscillators whose frequencies can shift slightly as they heat up or cool down. The most damning evidence, however, came from a more detailed analysis of the signal's frequency structure. When they looked at data from other days, they found signals at frequencies that were integer multiples or harmonics of the BLC-1 frequency. This is a classic fingerprint of human-made electronics. Natural astrophysical sources do not produce harmonic signals like this. The final nail in the coffin came from analyzing the signal's behavior when the telescope was pointed in a slightly different direction. They discovered that the signal was still present, albeit much weaker, even when the telescope was not pointed at Proxima Centauri. This proved conclusively that it was local interference, a form of RFI that was incredibly sneaky and had managed to slip through the initial filters. The ultimate conclusion, published over a year after the initial detection, was that BLC-1 was almost certainly human-made radio frequency interference from right here on Earth, likely from a faulty electronic device or a low-power transmitter within a few hundred kilometers of the telescope. It was a false alarm, but an incredibly sophisticated and educational one. BLC-1 stands as a perfect case study in the extreme difficulties of modern SETI. It represents a new class of interference that is becoming increasingly common as our own technology becomes more complex. Signals that are transient, that drift in frequency, and that can cleverly evade our best filters. This event didn't represent a failure, it was a vital success for the field. It proved that our verification protocols work, that our scientific skepticism is our greatest tool, and that we are developing the analytical muscles needed to identify the real thing when, or if, it finally arrives. The search continues, wiser and more prepared than ever before. While the meticulous search for radio signals from nearby stars like Proxima Centauri yielded frustrating false alarms, another cosmic mystery was unfolding that captured the public's imagination in an entirely different way, one centered not on what we might be hearing but on what we were clearly seeing. This brings us to the enigma of KIC 8462852, more famously known as Tabby star or the alien megastructure star. Discovered by citizen scientists in the data from NASA's Kepler Space Telescope, this star didn't have a strange radio signal, it had a bizarre and unprecedented light curve. Kepler's mission was to find exoplanets by detecting the telltale, periodic dips in a star's brightness that occur when a planet transits or passes in front of it. These dips are usually tiny, predictable, and symmetrical. Tabby's star was none of those things. It exhibited massive, irregular dimming events where its light output would plummet by up to 22%, a depth that is utterly incredible. To put that in perspective, a Jupiter-sized planet would only block about 1% of a sun-like star's light. Whatever was causing this was enormous, and it was not moving in a clean, orbital pattern. The most tantalizing and media-friendly theory proposed was that we were witnessing a vast, under-construction alien megastructure, perhaps a Dyson swarm, a colossal collection of energy-capturing satellites or panels encircling the star, built by a Type II civilization on the Kardashev scale to harness its entire energy output. The irregular, sharp dips in light could be explained by swarms of these constructs of different shapes and sizes, passing in front of the star in a chaotic, non-periodic manner. It was a breathtaking science fiction-like idea that instantly fired global curiosity. But science, of course, requires more than just a compelling narrative. It demands evidence. And if a civilization were capable of building such an immense project, it stood to reason that they might be using other forms of technology we could detect, such as powerful radio transmitters for communication or even propulsion systems for their construction projects. This line of thinking prompted a rigorous and dedicated search for any associated artificial radio signals, a search that ultimately returned a profound and telling silence. Major radio telescopes around the world, including the massive Green Bank Telescope in West Virginia and the coordinated dishes of the Allen Telescope Array in California, were pointed at Tabby's star for hundreds of hours, listening across a wide range of frequencies. The search was not for a message per se, but for any sign of technology. Scientists looked for two primary types of signals: narrowband transmissions, which would be the hallmark of a deliberate beacon, and broadband signals, which could be a byproduct of powerful energy use, like the leakage from intense radar systems or the propulsion of spacecraft. The results from these exhaustive campaigns were uniformly negative. No narrowband signals were found that exhibited the characteristics of an artificial beacon. No significant broadband emissions were detected that were inconsistent with the star's natural radio quietness. This radio silence is far from a boring non-discovery. It is a powerful piece of evidence that effectively rules out certain classes of hypothetical advanced civilizations. It tells us that if there is an intelligent cause for the dimming, it is not a society that is currently flooding the radio spectrum with communication signals or massive energy projects in the ways that we, as a technological civilization, can easily recognize. They are not broadcasting in a manner we can receive, or perhaps they are using a technology for communication that is so advanced it is entirely unrecognizable to us, something beyond our current understanding of physics. The absence of radio waves pushed the likely explanation firmly back into the realm of natural astrophysics, forcing scientists to double down on finding a solution that didn't involve aliens. And indeed, natural explanations have steadily gained support, with the most compelling one involving a vast, uneven cloud of dust. Subsequent observations found that the star's dimming was more pronounced at blue wavelengths than at red ones. This is a classic signature of light scattering off dust grains, the same phenomenon that makes our sun appear red at sunset as dust in the atmosphere scatters the blue light. This evidence pointed toward a family of natural causes, such as the aftermath of a cataclysmic planetary collision that left a sprawling, chaotic debris field in orbit, or a giant, fractured comet or swarm of comets on a long, eccentric orbit, periodically shedding vast amounts of dust and grit as they swing close to the star. The current scientific consensus leans heavily toward these dusty scenarios. The story of Tabby's star serves as a crucial lesson in the scientific process. It demonstrates how a single, bizarre observation can spark incredible creativity and speculation, but it is the follow-up multi-wavelength investigation, including the critical absence of expected evidence, that guides us closer to the truth, even if that truth is less sensational than a galaxy-spanning civilization. It shows that sometimes the most important discovery is not finding something, but definitively ruling something out, allowing us to focus our search for answers where they are most likely to be found. Just as the predictable rhythm of FRB 1891-6 gave us a cosmic clock to study, the discovery of another repeater turned the volume up to 11, refusing to ever be ignored. Meet FRB 1925-20, an absolute powerhouse of a signal that doesn't just repeat, it practically screams for attention, and it never ever shuts up. Discovered in 2019 by the 500-meter aperture spherical radio telescope, or FAST, in China, this source is located in a dwarf galaxy about 3 billion light-years away. But unlike other FRBs that have quiet, dormant periods, this one is relentlessly active, firing off bursts with a frequency and consistency that is almost unrivaled. On its most active days, it can produce hundreds of bursts in a single 24-hour period. It is, by every measure, the most prolific repeater we have ever found, a hyperactive child in the cosmic playground that simply cannot sit still. Its extraordinary behavior doesn't stop with the bursts themselves. When astronomers pointed other telescopes at its location, they discovered something even more astonishing. A faint but steady and constant radio glow emanating from the exact same spot. This is what's known as a persistent radio source, or PRS. Think of it like a campfire. The powerful millisecond FRB bursts are like someone throwing a whole can of gasoline onto the flames, creating a brilliant explosive flare. But even between these dramatic eruptions, the campfire itself continues to smolder, emitting a low, constant heat. This persistent radio source is that smoldering ember, a never-ending whisper of radio energy that underlies the violent shouts of the burst. This combination, a hyperactive repeater sitting on top of a persistent radio source, was thought to be a 1 in a billion oddity, until scientists realized we had seen this exact pairing before. FRB 1200-1102, the original repeater that shattered the cataclysm model, also has its own persistent radio source. Now we had 2 of them. Finding a second example of this bizarre pairing was a monumental breakthrough. In science, 1 is an anomaly, 2 is a pattern. This strongly suggested that FRB 1200-1102 and FRB 1925-20 are not just random oddities. They might represent an entirely distinct class of fast radio burst, one with a unique and powerful engine that can both fire off repeated bursts and sustain a constant radio glow. So what could possibly power such a relentless dual-output system? The leading theory points to an incredibly young and energetic magnetar that is still swaddled in its own cosmic crib. When a massive star goes supernova, it doesn't just vanish. It leaves behind a rapidly spinning, intensely magnetic neutron star, and it also creates a vast, expanding cloud of debris and ionized gas known as a supernova remnant. This remnant is a turbulent, dense nebula packed with energetic particles and powerful magnetic fields. The theory proposes that FRBs like these 2 are newborn magnetars, perhaps only decades or centuries old, still embedded deep within the hot, dense plasma of their freshly formed supernova remnants. This environment is the key to explaining both phenomena. The persistent radio source, the constant glow, is believed to be the radio emission from this surrounding nebula itself, energized by the powerful winds and outbursts from the young, hyperactive magnetar at its heart. The incredible burst activity could be driven by the magnetar's violent adjustment to its new life. Its crust could be cracking under immense magnetic stress, or it could be accreting material from the dense remnant cloud around it, triggering massive eruptions. This young magnetar model elegantly explains why these 2 FRBs are so exceptionally active and why they have a persistent glow that others lack. They are simply in a more extreme, energetic, and chaotic phase of their life cycle. This discovery forces us to consider that the universe of fast radio bursts might be more diverse than we ever imagined. Perhaps there isn't just one single cause for all FRBs. Maybe some, like the one-off bursts, are indeed the final death cries of stellar collisions, while others, like the rhythmic FRB 1891-6, are older, more stable systems in binary orbits. And then there is this special class, the persistent repeaters, representing the tumultuous, brilliant, and short-lived infancy of the most magnetic objects in the cosmos. FRB 1900-2520, with its non-stop activity and its ever-present radio hum, gives us a front-row seat to the chaotic and dramatic nursery of a newborn stellar monster, offering a priceless window into the most energetic teenage years a cosmic object can have. While our focus has been on the chaotic and unpredictable bursts from the depths of space, the history of cosmic signals holds a pivotal moment when the universe seemed to offer not a shout or a whisper, but a perfect metronomic beat, a signal so clock-like it seemed impossible for it to be natural. We travel back to 1967, to the chilly, open fields of the Mullard Radio Astronomy Observatory in Cambridge, England. A brilliant doctoral student named Jocelyn Bell Burnell was painstakingly reviewing miles of chart paper data from a new radio telescope she had helped build. The telescope was designed to study quasars, but buried in the endless, squiggly lines of cosmic static, Bell noticed something peculiar, a faint, recurring bit of scruff. It was a signal that appeared and disappeared with the precise regularity of a celestial timepiece, pulsing exactly every 1.337 seconds. The sheer perfection of its timing was utterly baffling. Nothing in the known natural world behaved with such machine-like precision. The pulses were too fast and too regular to come from something as large as a star, and they didn't match the behavior of any known variable radio source. In a field where scientists are trained to eliminate the most outlandish possibilities first, the team, half jokingly and half seriously, had to consider the unthinkable. They labeled the source LGM-1 in their private notes, with LGM standing for Little Green Men. The notion that this could be an interstellar beacon from an advanced civilization was not a publicity stunt. It was a genuine, if disconcerting, hypothesis. Could they have stumbled upon a galactic lighthouse, a navigational buoy placed by a distant intelligence to mark their territory or communicate across the void? This period was one of immense professional and personal tension for Bell and her supervisor, Anthony Hewish. The idea was so extraordinary that they kept it a secret for months, terrified of making a public announcement only to discover it was a mundane terrestrial interference or, worse, a technical fault in their own instrument. They whimsically dubbed the other three such signals they found LGM-2, 3, and 4, all the while working tirelessly to rule out every possible explanation. The true nature of the signals was finally revealed not by finding a message in the pulses, but by discovering a second, entirely separate source pulsing at a completely different rate in another part of the sky. You might build one interstellar beacon, but you wouldn't build several, each with its own unique and meaningless rhythm. The signals were natural, not artificial. They were, in fact, the first detected pulsars rapidly spinning neutron stars, the ultra-dense, city-sized corpses of massive stars that had died in supernova explosions. A pulsar is a cosmic lighthouse. As this neutron star spins, its incredibly powerful magnetic field, trillions of times stronger than Earth's, funnels beams of intense radio waves out from its magnetic poles. If these poles are misaligned with its rotation axis, these beams sweep through space like the beam of a lighthouse. From our vantage point on Earth, we see a brilliant, flashing pulse of radio energy each time that beam sweeps across our line of sight. The timing is so precise because it is governed by the rotation of this super-dense, perfectly balanced stellar cinder. The clockwork regularity is a direct result of the conservation of angular momentum, the same physics that keeps a spinning top upright, acting on an object of unimaginable density. The discovery of pulsars was a monumental achievement in astrophysics, earning Anthony Hewish a Nobel Prize, an award that famously overlooked Jocelyn Bell Burnell's critical role, a controversy that still resonates in the scientific community today. But beyond the Nobel snub, the LGM episode left a profound and enduring legacy for the search for extraterrestrial intelligence. It serves as the ultimate cautionary tale and a masterclass in scientific skepticism. It established a golden rule for SETI: any signal that is perfectly periodic and unchanging is almost certainly natural. An artificial signal designed for communication would likely contain information, meaning its pattern would be complex and variable, not a simple, endless repetition of an identical pulse. The universe is filled with natural clocks, pulsars, binary star systems, rotating asteroids, and their perfect rhythms are now the first things scientists rule out when hunting for a true technosignature. Yet, the story of the LGM pulsars is also one of thrilling possibility. It proved that the cosmos is capable of generating phenomena so strange and so precise that they can truly challenge our assumptions and fire our imaginations. It taught us to keep our minds open to the extraordinary while grounding our conclusions in rigorous evidence. Every time a new pulsar is discovered, its unwavering beat is a reminder of that historic moment when we dared to wonder if we were not alone, and in doing so, unlocked a deeper understanding of the extreme and beautiful physics that governs the life and death of stars. While the disciplined search for alien beacons often focuses on distant, unknown stars, one of the most electrifying potential signals seemed to come from a place that felt almost familiar, a near twin of our own sun. In 2015, a team of Russian astronomers using the Ratan 600 radio telescope reported a powerful, intriguing signal that appeared to originate from a star called HD 164595, located just 95 light-years away in the constellation Hercules. This wasn't a random point of light. This star held a special significance for planet hunters. It is a near-perfect solar analog, a star almost identical to our Sun in size, mass, and age. Even more compelling, we already knew this star had at least one planet, a Neptune-sized world orbiting very close in. The possibility of more, potentially Earth-like planets in its habitable zone made it a prime candidate in the search for life. So when a strong, narrowband signal was detected at 11 GHz, the excitement was immediate and intense. The signal itself was a brief burst, lasting only about 2 seconds, but its apparent strength was what truly captured attention and ignited speculation. The Russian team calculated that if this signal were being broadcast in all directions equally, an omnidirectional transmission, the energy required would be staggering. To pump out a signal powerful enough to be detected across 95 light-years of interstellar space would demand a civilization capable of harnessing the entire energy output of its home star, a feat that would place them squarely as a Type II civilization on the Kardashev scale. This was the stuff of classic science fiction, a society so advanced they had built a Dyson sphere or similar megastructure to fuel their galactic ambitions. But there was another, more plausible interpretation. If the signal was not a general broadcast to the galaxy, but a tightly focused beam deliberately aimed at our solar system, the energy requirements dropped dramatically. In that targeted scenario, a signal we could detect might only require the energy equivalent of all the sunlight that falls on Earth, a task still far beyond our capabilities, but not unimaginable for a civilization a few hundred or thousand years more advanced than our own. This distinction between an omnidirectional shout and a targeted whisper became the central point of debate, transforming the detection from a curious blip into a serious topic of discussion among SETI scientists. The story broke into the public sphere a year later, in 2016, and the media frenzy was instantaneous. Headlines around the world proclaimed the possible discovery of an alien signal from a sun-like star. The SETI community, however, responded not with celebration, but with its trademark rigorous skepticism. the Breakthrough Listen initiative quickly mobilized, training the powerful Green Bank Telescope in West Virginia and the Allen Telescope Array in California onto HD 164595. They listened intently across a wide range of frequencies, searching for any repeat of the signal or any other sign of artificial transmission. At the same time, other astronomers began a meticulous forensic analysis of the original detection, digging into its specific properties and the exact coordinates from which it came. This thorough investigation revealed a far more mundane, yet incredibly instructive truth. The most likely culprit, it turned out, was not a distant civilization, but a much closer and entirely human source, a military satellite. The signal's frequency of 11 GHz falls within a band commonly used for downlinking data from reconnaissance and surveillance satellites. The original Russian observation also coincided precisely with the passage of a known classified Russian military satellite, Cosmos 2496, which was passing through that exact patch of sky at that exact time. The signal's characteristics, its brevity, its specific frequency, and its timing all pointed toward an interception of a routine, secretive satellite transmission that the Russian astronomers, through no fault of their own, had not accounted for in their data filters. The grand hypothesis of a Type II civilization collapsed under the weight of Occam's razor, replaced by the simple explanation of terrestrial technology. The story of the HD 164595 signal, sometimes nicknamed the tattoo signal, stands as a perfect modern parable for the challenges of 21st century SETI. It underscores a new and growing problem. Our own planet is now enveloped in a thick shell of radio frequency pollution from thousands of satellites, each a potential source of false hope. Distinguishing a genuine cosmic call from the endless chatter of our own technology is becoming one of the most difficult technical hurdles in the field. This event didn't represent a failure of science, but a demonstration of its self-correcting nature. The initial excitement was channeled into a swift and decisive verification process, which efficiently ruled out an extraordinary claim with ordinary evidence. It serves as a crucial reminder that the universe is a noisy place, and the loudest signals are often the ones we've brought with us. Just when we thought we had a handle on the extreme distances of fast radio bursts, the universe decided to throw us a curveball from right in our own cosmic backyard. For years, the defining characteristic of FRBs was their incredible extragalactic origin, with dispersion measures placing them billions of light-years away in the deep, ancient universe. That was the rule, the established pattern that all our theories were built upon. Then along came FRB 2020-00120E, a signal that broke all the rules and sent a shockwave through the astrophysics community. Detected in January 2020, this FRB didn't come from a distant dwarf galaxy. Its dispersion measure was astonishingly low, pointing to a source a mere 11.7 million light-years away. That's a stone's throw in intergalactic terms, placing it well within our local group of galaxies, but the real stunner was its precise cosmic address. This incredibly powerful flash of energy was traced back with unprecedented accuracy to a specific and utterly surprising location: the majestic globular cluster known as Messier 81 or M81. This was a discovery that fundamentally challenged our understanding of what could create these phenomenal bursts. Globular clusters are like the ancient retirement homes of our galaxy. They are densely packed, spherical swarms of hundreds of thousands of stars, all gravitationally bound together. Crucially, the stars in these clusters are incredibly old, among the oldest in the entire universe, having formed over 10 billion years ago. They are metal-poor, meaning they lack the heavy elements forged in later generations of stars. This environment is the last place anyone expected to find the engine for an FRB. The prevailing theory, strongly supported by repeaters like FRB 1200-1102, pointed to young, highly magnetized neutron stars called magnetars. These stellar remnants are the products of recent massive supernova explosions, the kind that happen in vibrant, star-forming regions where massive, short-lived stars are born and die in spectacular fashion. An ancient globular cluster where massive stars died off eons ago should be a magnetar ghost town. Finding an FRB here was like finding a roaring newborn baby in a quiet, centuries-old library. It simply didn't belong. This glaring contradiction forced astrophysicists to go back to the drawing board and consider a whole new set of possibilities for what could be powering this galactic intruder. If it's not a young magnetar, what incredibly energetic object could be lurking in this stellar senior community? One compelling alternative theory points to a white dwarf merger. White dwarfs are the Earth-sized, dense cores left behind when lower mass stars like our Sun die. In the crowded dance of a globular cluster, binary white dwarf systems could be driven to merge through gravitational interactions. The collision of two such dense objects could create a transient super-Chandrasekhar mass object that might collapse directly into a neutron star, releasing a tremendous burst of energy in the process, a burst that could manifest as an FRB. Another fascinating possibility is the existence of an unusual binary system, perhaps involving a white dwarf and a neutron star. The neutron star, an ancient relic itself, could be accreting material from its companion white dwarf. If this accretion process becomes unstable, it could trigger massive magnetic reconnection events or collapses on the neutron star's surface, producing the powerful radio burst we detect. There's even a more exotic, though less likely, hypothesis: a black hole or neutron star interacting with a dense planetary mass object that was torn from a star in a long-ago close encounter. The significance of FRB 2020-00120E cannot be overstated. It is a powerful reminder that nature is far more inventive than our models, and it single-handedly proved that the FRB phenomenon is not monolithic. There is not one single path to creating these bursts. There are likely multiple roads, multiple engines, operating in vastly different cosmic environments. This one detection from an ancient cluster tells us that the universe can manufacture these extraordinary flashes through channels we are only beginning to imagine, using stellar ingredients and processes we thought were long past their expiration date. It transformed FRBs from a purely extragalactic mystery into a potential galactic one as well, raising the thrilling possibility that similar, nearby sources could be lurking undetected right here in the Milky Way, waiting for the right moment to flash their immense power and once again reshape our understanding of the cosmos. Amidst the search for signals from distant stars and the explosive bursts from dying stars, one of the most profound and controversial claims emerged not from a radio telescope, but from the most precise maps of the universe's birth ever created. This is the story of the so-called Periton microwave signal, a purported anomaly in the data from NASA Wilkinson Microwave Anisotropy Probe, or WMAP, and later the European Space Agency's Planck satellite. These missions had a singular, monumental goal: to capture the afterglow of the Big Bang itself, known as the cosmic microwave background. This faint, cold radiation is the oldest light in the universe, a snapshot from when the cosmos was just 380,000 years old, a swirling plasma of particles and energy that had finally cooled enough for light to travel freely. By mapping the tiny temperature fluctuations in this background patterns of slightly warmer and cooler spots, cosmologists can read the story of the universe's infancy, understanding its composition, its rate of expansion, and its very origins. Within this incredibly detailed map, some researchers claim to have found something that shouldn't be there. The contention centered on a specific type of pattern in the microwave light, a peculiar non-Gaussianity, and certain alignments of hot and cold spots that seem to defy the standard model of inflation. The theory that the universe underwent a period of exponential expansion just after the Big Bang. The most radical interpretation put forward by a small group of physicists was that these patterns were not from our Big Bang at all, but were actually echoes or imprints from a previous cosmic cycle, a universe that existed before our own. The name given to this hypothetical signal, periton, comes from the Greek for previous and tone or stretch, suggesting a relic from a prior epoch of spacetime. It was a breathtaking idea, suggesting our universe is just one link in an infinite chain of cosmic death and rebirth, a concept known as the conformal cyclic cosmology. The mainstream cosmological community, however, approached this claim with extreme and well-founded skepticism. The primary issue lies in the Herculean task of data processing. The raw data from satellites like WMAP and Planck is not a clean picture of the early universe. It is a messy composite, heavily contaminated by foreground emissions from our own Milky Way galaxy, dust, gas, and synchrotron radiation that must be meticulously modeled and subtracted using complex algorithms. The process of peeling away these foreground layers to reveal the pristine cosmic microwave background beneath is incredibly delicate. A tiny error in the model, an imperfect understanding of galactic dust properties, or a subtle instrumental effect could easily introduce a spurious pattern that looks tantalizingly real. The consensus among most cosmologists is that the periton signal is far more likely to be one of these artifacts, a ghost in the machine created during the arduous cleanup process, rather than a genuine whisper from a pre-Big Bang universe. This debate perfectly illustrates the immense challenge of working with massive, complex datasets in modern astrophysics. We are now in an era where our instruments are so sensitive that the line between a universe-shattering discovery and a simple statistical fluke is vanishingly thin. When you collect petabytes of data and run millions of statistical tests on it, you are virtually guaranteed to find a few anomalies purely by random chance. This is known as the look elsewhere effect. If you search for a strange pattern in enough different ways and in enough different places, you will eventually find something that appears significant, even if it is just noise. The scientific method is designed to guard against this. An extraordinary discovery requires not just a strange signal, but one that is independently verified by different instruments using different methodologies, and one that robustly survives every single attempt to prove it wrong. The periton signal, for all its provocative allure, has not yet passed that rigorous gauntlet of tests. It stands as a powerful lesson in humility, reminding us that our desire to find profound answers must always be tempered by a rigorous commitment to methodological skepticism, ensuring that the stories we tell about the cosmos are built on the most solid and verified foundations we can possibly construct. Just when we thought we had mapped the entire cosmos through the afterglow of its birth, astronomers stumbled upon a motion so vast and so strange it seemed to defy the very foundations of modern cosmology. This isn't a flash of light or a radio pulse, but a subtle, persistent current in the flow of the universe itself, a phenomenon known as the dark flow. The story begins with our most precise map of the infant universe, the cosmic microwave background. This radiation is the ultimate cosmic rest frame, the background against which all motion should be measured. According to the standard model of cosmology, the motion of galaxy clusters should be random and isotropic, like leaves scattered by the wind, with no preferred direction on the largest scales. The overall expansion of the universe, driven by dark energy, should be the only coherent large-scale motion. But when scientists studied the subtle distortions in the CMB caused by the motion of massive galaxy clusters, an effect known as the kinematic Sunyaev-Zeldovich effect, they found something that shook this assumption to its core. The data, first from the Wilkinson microwave anisotropy probe and later analyzed with data from the Planck satellite and X-ray observatories, suggested that hundreds of galaxy clusters were not moving randomly. Instead, they were all streaming in the same direction at astonishing speeds of nearly 2 million miles per hour. This was not a local effect. The flow appeared to extend to the very limits of the observable universe, a coordinated motion on a scale so immense it should be impossible. It was as if every ship in a vast, endless ocean was being pulled by the same invisible current. The immediate and most thrilling explanation for this dark flow is the gravitational pull of something immense that lies beyond the horizon of our observable universe. The observable universe is a bubble centered on us, limited by the distance light has been able to travel since the Big Bang. But the entire cosmos is almost certainly much, much larger than this bubble. The theory proposes that a colossal, unseen concentration of mass, a superstructure of galaxies, or a density fluctuation of staggering proportions exists in this unobservable realm. Its gravitational influence would reach across the void, tugging on everything within our visible horizon and creating this coherent bulk flow. This idea is both exhilarating and humbling, suggesting that the entire structure of our known universe might be influenced by geography we can never directly see, a cosmic neighborhood whose full extent remains a profound mystery. Of course, such an extraordinary claim faces intense and necessary scrutiny. The primary alternative is that the dark flow is not a real physical phenomenon, but a systematic error buried in the incredibly complex process of analyzing the data. Detecting the minute kinetic SZ effect requires peeling away countless layers of foreground contamination from our own galaxy and accounting for every possible instrumental artifact. Critics argue that even a tiny, unaccounted-for bias in this data processing could create the illusion of a bulk flow where none exists. The statistical significance of the result has been hotly debated within the cosmology community, with some independent analyzers failing to confirm the effect at the same strength or even at all. This ongoing debate is a perfect example of science at its most difficult frontier, where the signal being hunted is at the very limit of what our technology and our statistical methods can reliably detect. Whether the dark flow is ultimately confirmed as a real phenomenon or dismissed as a data ghost, its investigation has already served a vital purpose. It acts as a powerful stress test for our standard cosmological model, the lambda cold dark matter model. This model has been spectacularly successful at explaining a vast array of observations, but the potential existence of a dark flow suggests there might be a crack in its foundation, a hint that our understanding of the universe on the very largest scales is still incomplete. It pushes our instruments and our theories to their absolute limits, forcing us to question if we are truly seeing the whole picture or just a fraction of a much grander, and perhaps even more mysterious cosmic tapestry. While we grapple with the grand, flowing currents of the dark flow on the very largest scales, our search for cosmic mysteries also zeroes in on specific, brilliant points of light that defy categorization, bringing us to a catalogue of enigmas written in the most energetic language the universe speaks, gamma rays. For over a decade, the Fermi Gamma Ray Space Telescope has been our silent sentinel in orbit, meticulously mapping the high-energy sky. It has revealed a universe shimmering with powerful sources, from the frantic spins of pulsars to the monstrous jets erupting from supermassive black holes in active galaxies. But amidst these known celestial landmarks, Fermi has also pinpointed hundreds of sources that are utterly anonymous. These are the unidentified Fermi sources, points of intense gamma-ray light that stubbornly refuse to match up with any known type of object in any other wavelength of light. They are cosmic question marks glowing with the power of unanswered questions. The mystery lies in their isolation. When astronomers point the world's most powerful optical, infrared, and radio telescopes at the coordinates of these gamma-ray hotspots, they often find nothing. Or at least nothing that should be capable of producing such prodigious amounts of energy. It's as if you were given the address of a powerhouse generating enough electricity for a major city, but when you arrive, you find only an empty field. The energy is undeniably there, recorded by Fermi's exquisite detectors, but its source remains a complete and total enigma. This has forced scientists to consider two broad, fascinating possibilities: Either we are seeing entirely new classes of natural astrophysical objects, or we are glimpsing something far more speculative. On the natural side, the leading theories are as compelling as they are varied. One strong candidate is that these sources could be the long-sought-after signature of dark matter annihilation. If dark matter is made of weakly interacting massive particles, or WIMP, then in regions where it is densely concentrated, these particles could occasionally collide and annihilate each other, converting their mass directly into energy and producing a burst of gamma rays. An unidentified source, especially one that appears extended or fuzzy, could be the glow from a dense clump of dark matter at the center of a dwarf galaxy or a dark matter halo. Another natural explanation points to a previously unrecognized population of extreme pulsars. Perhaps these are pulsars that are older, more isolated, or beaming their energy in a way we haven't learned to detect in other wavelengths, making them visible only through their fierce gamma-ray glow. But the sheer strangeness of these sources also opens the door to a more speculative and far more thrilling line of thinking. Could some of these unidentifiable beacons be evidence of astroengineering on a scale so vast it defies human comprehension? One hypothetical concept that has captured the imagination of theorists is the idea of a gamma-ray laser or gracer powering an interstellar light sail. An advanced civilization, a Type 2 on the Kardashev scale, might need a truly immense amount of energy to propel spacecraft between the stars. A light sail, pushed by the momentum of photons, is a theoretically viable method, but it requires an incredibly powerful and focused beam of light to achieve relativistic speeds. A gamma-ray laser would provide that focus and power, and the beam itself, if it were to accidentally or intentionally sweep across our solar system, could register in Fermi's data as a transient, incredibly bright, and completely unidentified point source. The idea is that we might not be looking at an object at all, but rather the ephemeral flash of a cosmic engine's exhaust beam, a signature of directed energy so advanced it mimics a natural astrophysical phenomenon. The scientific community, of course, heavily favors the natural explanations, with dark matter and novel pulsar types at the top of the list. The process of science is one of patiently eliminating the mundane before embracing the extraordinary. Yet, the enduring mystery of these hundreds of unassociated sources serves as a powerful and humbling reminder of how much we have yet to learn about the high-energy universe. Each one is a target for further investigation, a puzzle waiting for a new telescope or a fresh analytical technique to solve it. They represent the cutting edge of discovery, where the known map of the cosmos ends and the real adventure into the unknown begins, reminding us that our greatest discoveries often start not with an answer, but with a beautiful, tantalizing, and unresolved question. While our search for cosmic intelligence has primarily focused on the radio whispers and gamma-ray shouts of advanced technology, some of the most compelling evidence might not be in the messages a civilization sends, but in the energy it simply cannot hide. This shifts our investigation to a completely different part of the electromagnetic spectrum, the quiet thermal glow of infrared light. The concept was first proposed by physicist Freeman Dyson in the 1960s. He theorized that a civilization advanced enough to harness the total energy output of its home star would eventually need to build a vast swarm of energy-collecting satellites or a solid shell, a Dyson sphere, encircling the star. While this megastructure would capture the star's visible light, it could not violate the laws of thermodynamics. The energy has to go somewhere. According to Dyson, that somewhere would be re-radiated as waste heat, a significant, detectable excess of infrared radiation emanating from what would otherwise look like a strangely dim star. This became the holy grail for hunters of Kardashev Type 2 civilizations, a way to find them not by what they are saying, but by the immense thermodynamic signature of their existence. The quest for these infrared anomalies has turned up numerous candidates over the years, stars that exhibit that telltale excess of IR radiation. but one star, known by its algorithmic designation Gaia 16I, presented a mystery that was far more dynamic and bizarre than a simple thermal glow. Discovered by the European Space Agency's Gaia satellite in 2016, this object didn't just have an infrared excess, it was undergoing a dramatic and complex dimming event. Its light curve was unlike anything astronomers had seen before. Instead of the clean, symmetrical dip of a transiting planet, Gaia 16I's brightness dropped in a series of sharp, irregular, and deep declines, as if something of varying shapes and opacities was repeatedly passing in front of it. The initial data was so strange that it immediately triggered follow-up observations from telescopes all over the world, creating a rich, multi-wavelength portrait of a truly unique event. The most compelling natural explanation, and the one that has gained widespread acceptance, involves an intricate celestial dance. Gaia 16I is not a single star but a binary system. The star that was dimming is likely being periodically eclipsed by a massive, swirling cloud of gas and dust that is itself orbiting a second, unseen companion, possibly another star or a large planet. This isn't a simple, solid object transiting. Think of it more as a vast, misshapen cloud of cosmic soot and gravel, a protoplanetary disk or a debris field with a complex, clumpy structure. As this cloud orbits its host, its dense knots and uneven edges pass in front of the star from our viewpoint, causing the unpredictable and sharp dips in brightness. This model elegantly explains the strange light curve without needing to invoke any intelligence. It paints a picture of a young, still-forming solar system where planets are coalescing from a turbulent and messy disk of material, a natural and violent process of creation. However, for a brief and thrilling moment, the megastructure hypothesis was on the table. The irregular, non-periodic nature of the dimming events was reminiscent of the much more famous Tabby star. Could this be evidence of a Dyson swarm under construction? The idea was that a civilization building such a vast array would likely not complete it all at once. Different sections, panels, or clusters of collectors would be placed in orbit at different times, creating a collection of objects with varied sizes, shapes, and opacities. Their transits would be chaotic, non-periodic, and would cause exactly the kind of complex dimming pattern observed in Gaia 16I. The infrared excess, the waste heat from all this captured stellar energy, would be the final piece of corroborating evidence. It was a narrative that fit the data disturbingly well, a tantalizing possibility that we were witnessing the greatest construction project imaginable. Yet, science in its methodical way favored the natural over the supernatural. Detailed spectroscopic observations ultimately provided the key evidence. As the dimming events occurred, astronomers were able to analyze the star's light as it filtered through the transiting material. They found clear signatures of scattered light, a phenomenon that occurs when light passes through a cloud of small particles, exactly what you would expect from a dusty disk. Furthermore, no significant or unusual infrared excess was ever conclusively linked to the dimming event itself. The system's IR signature was consistent with what is expected from a normal young stellar object surrounded by dust. The collaborative verdict was clear. Gaia 16I was a spectacular example of natural astrophysics, a cosmic eclipse by a complex, dusty cloud, and not the signature of an alien megastructure. The story of Gaia 16I is a perfect microcosm of the entire search for Dyson spheres. It demonstrates the rigorous process of scientific discovery, an initial, extraordinary anomaly, the formulation of both natural and artificial hypotheses, and the patient gathering of evidence that ultimately points toward a natural, if spectacular, explanation. These infrared candidates and their associated dimming events are not disappointments. They are the training grounds for our future discoveries. They force us to refine our models to better understand the incredible diversity of natural phenomena that can mimic the signs of intelligence. They teach us that the universe is capable of producing wonders so strange they can fuel our grandest imaginings. while simultaneously grounding our search in the meticulous, evidence-based work that will one day, perhaps, separate the truly artificial signal from the cosmos's endless capacity for natural amazement. From the grand, sweeping mysteries of dark flow and the infrared whispers of hypothetical megastructures, we now turn to a signal that was both incredibly brief and strangely recursive, a cosmic event that seemed to defy the very way we understand energy to travel through space. This brings us to the peculiar case of the boomerang signal, a one-off radio burst detected from a region known as NGC 2264, also called the Christmas tree cluster due to its festive arrangement of bright young stars. This isn't just a pretty patch of sky, it's a stellar nursery, a chaotic and dense cloud of gas and dust where new stars are being born in a storm of gravitational collapse and intense radiation. It was from this vibrant cosmic cradle that a unique signal emerged, not just for its power but for its utterly bizarre behavior. It didn't just arrive once, it seemed to come back for an encore. The event was captured as a classic millisecond duration fast radio burst, a powerful spike of radio energy, but the data held a surprise. After the initial pulse, there was a second distinct pulse. This wasn't random static or an unrelated event. Analysis showed this secondary signal was a near-perfect replica of the first, but it was significantly fainter and, crucially, it arrived a fraction of a second later. It was as if the signal had hit a cosmic backboard and bounced back toward us, creating a clear and unmistakable echo. This boomerang effect was unprecedented. In the clean vacuum of space, radio waves are supposed to travel in straight lines. A single brief explosion should produce a single brief signal. So what could possibly cause a single burst to split into two and arrive at two different times? Astronomers were presented with a fascinating puzzle, and the solutions all point to the complex and often messy nature of the interstellar medium. The thin soup of gas, dust, and plasma that fills the space between stars. One compelling theory involves a natural cosmic lens. Imagine a massive, cold cloud of molecular gas and dust drifting between us and the source of the FRB. If this cloud has a dense, compact core, it could act as a gravitational lens. According to Einstein's theory of general relativity, a massive object can warp the fabric of spacetime around it, bending the path of light and other radiation. In this scenario, the initial powerful burst traveled directly to us on a straight-line path, but a portion of the radio waves traveled on a slightly different route, bending around this dense interstellar cloud. This longer, curved path would mean those waves had to travel a greater distance, causing them to arrive at our telescopes a split second later and appearing as a fainter, delayed echo of the original event. We wouldn't be seeing two events, but one event seen twice, thanks to the gravity of an invisible cosmic lens. A second, equally plausible theory suggests a more direct interaction. What if the FRB itself was powerful enough to energize a large, nearby object, perhaps a dense planet or a cloud of ionized gas orbiting the same star? The initial blast of radio energy slams into this object, which then re-radiates a portion of that energy, effectively creating a reflective echo. The delay is simply the extra time it takes for the radio waves to travel from the original source to this reflective body and then onward to Earth. This would be the astronomical equivalent of shouting in a canyon and hearing your own voice bounce back from a distant cliff face. The main burst is your initial shout, and the echo is the sound returning from the canyon wall. A third possibility is even more profound, the double event theory. This proposes that the two pulses are not a copy, but are in fact two separate bursts originating from the exact same cataclysm. Imagine a neutron star experiencing a massive starquake, a rupture on its ultra-dense crust that releases a first, tremendous blast of energy. Milliseconds later, the destabilized star undergoes a second related collapse or magnetic reconnection event, triggering another, slightly less powerful burst. From our distant vantage point, these two distinct explosions would appear as a primary signal followed immediately by its weaker twin, creating the illusion of a single event with an echo. This theory suggests the boomerang wasn't an illusion of propagation, but a real double-barreled blast from a single, incredibly violent progenitor. The boomerang signal, though never repeated, serves as a critical reminder that the path between a cosmic event and our telescopes is never truly empty. The interstellar medium is not a perfect vacuum. It's a landscape filled with invisible obstacles, lenses, and potential mirrors that can distort, delay, and reshape the signals passing through it. This single, echoing burst highlights the incredible challenge of interpreting what we detect. It forces us to consider not just the source of the signal, but everything that lies in between, reminding us that sometimes the most fascinating part of the message isn't the content, but the complex and twisted journey it took to reach us. While we often look outward to distant galaxies for cosmic mysteries, one of the most powerful and bizarre radio signals known to science originates right here in our own solar system, emanating not from the Sun but from its largest planet. Jupiter, a colossal world of swirling gas, is more than a visual marvel. It is a radio powerhouse generating intense, coherent emissions that can actually be picked up by amateur astronomers with relatively simple equipment right here on Earth. This isn't a faint whisper or a random burst of static. It's a roaring, beam-like signal known as decametric radiation, and its story is one of a complex gravitational dance involving the planet's immense magnetic field and its tortured volcanic moon, Io. The sheer scale of Jupiter's magnetosphere is almost incomprehensible. If it were visible to the naked eye, it would appear larger than the full moon in our sky, a vast, invisible bubble of magnetic influence that stretches millions of miles into space, even occasionally engulfing the orbit of Saturn. Within this colossal magnetic environment, charged particles, electrons and ions, are trapped, accelerated to nearly the speed of light, and whipped along the planet's magnetic field lines. But the real catalyst for the radio symphony is Io. This moon is the most volcanically active body in the solar system, constantly spewing sulfur dioxide and other gases from its numerous volcanoes. These eruptions create a tenuous but constant torus, a donut-shaped ring of ionized plasma that follows Io's orbit around Jupiter. As Io plows through this very magnetosphere it helps to create, it acts like a colossal electrical generator. The moon's movement through Jupiter's powerful magnetic field induces an electric current of millions of amperes that flows along the magnetic field lines, connecting Io directly to Jupiter's polar regions. It is at these poles within vast magnetic flux tubes that the magic happens. The streaming electrons, forced to spiral along the curved magnetic field lines, are accelerated and generate powerful, coherent radio waves through a process known as cyclotron maser instability. This isn't just random radio noise, it's a highly polarized beam-like emission, a focused lighthouse beam of radio energy that sweeps through space as Jupiter rotates. For scientists involved in the search for extraterrestrial intelligence, or SETI, Jupiter's decametric radiation is far more than a planetary curiosity. It is a crucial natural laboratory and a vital cautionary tale. The signal possesses several characteristics that, if detected from a distant star, would set off every alarm bell for a potential artificial transmission. Its emission is highly polarized, meaning its radio waves are aligned in a specific, orderly pattern, a trait often associated with engineered transmitters. It is also narrowband and incredibly intense, bursting forth in powerful, sometimes periodic eruptions. Most tellingly, it is beam-like, meaning it is only detectable from Earth when Jupiter's rotating magnetic lighthouse points its beam directly at us. This creates a window of detectability, a period of activity that follows a predictable pattern based on the planet's rotation and Io's orbital position. This natural phenomenon provides a masterclass in how the universe can produce signals that perfectly mimic the expected signatures of technology without any intelligence behind them. It forces SETI researchers to develop ever more sophisticated filters and analytical tools to distinguish between a naturally occurring cosmic maser and a genuine artificial beacon. Jupiter teaches us that a signal's coherence, polarization, and periodicity are not, in themselves, proof of intelligence. They are merely clues that must be weighed against the complex backdrop of natural astrophysics. By studying this gas giant in our own backyard, we are essentially training our ears to hear the difference between the chaotic but patterned music of the cosmos and a single, deliberate note played by a composer somewhere in the dark. From the chaotic, echoing bursts and the predictable rhythms of distant galactic sources, our search for cosmic mysteries now takes us to the very heart of our own galaxy, where a fleeting signal pulsed with the steady, haunting regularity of a dying heartbeat. This is the story of GCRTJ 1745-3009, a name that belies one of the most peculiar and captivating transient events ever recorded. In the autumn of 2002, a radio telescope survey scanning the dense, mysterious region toward the galactic center detected something utterly unexpected. For a brief window of roughly 1 hour, a previously silent patch of sky came alive with a series of powerful, coherent radio bursts. But these weren't the random, millisecond flashes of a fast radio burst. They were periodic, arriving with a perfect metronomic beat every 77 minutes. It was as if a cosmic lighthouse had suddenly switched on, flashed its beam precisely 5 times, and then vanished into silence forever. Despite numerous and extensive follow-up observations over the subsequent years, this enigmatic source, nicknamed the bursting pulsar or the galactic center radio transient, has never been heard from again. What could possibly create such a brief yet perfectly rhythmic performance? The leading theories all point to the usual suspects of extreme astrophysics, but with a unique and puzzling twist. One compelling idea is that we witnessed a precessing neutron star. Imagine a spinning neutron star, its rotational axis slowly wobbling like a top about to fall over. This wobble or precession could cause its powerful beam of radio emission to sweep across our line of sight only during a very specific and temporary phase of its cycle. For that 1 hour in 2002, its lighthouse beam was pointed directly at Earth, and then it precessed away, taking its signal with it for what could be a cycle lasting centuries or longer. This would explain the perfect periodicity and the transient nature, but it requires a very specific and stable precession mechanism. Another fascinating hypothesis involves a magnetar, a neutron star with an unimaginably powerful magnetic field. In this scenario, the 77-minute period might not be the star's spin, which is typically measured in seconds, but the timescale of a slow, giant starquake or a sudden instability within its twisted magnetosphere. The star's incredibly rigid crust under immense magnetic stress could have fractured, releasing a burst of energy and accelerating particles that generated the radio burst. The 77-minute interval could represent the time it took for the magnetic stresses to build back up to the breaking point, triggering the next burst in a series until the system finally settled down. It was a temporary, self-limiting series of magnetic seizures on the surface of a stellar corpse. A third possibility introduces a partner in this cosmic dance, an unusual binary system. Perhaps the source is a neutron star in a highly elliptical orbit with a low-mass stellar companion. The 77-minute period could be the orbital period itself. The radio bursts might only occur during a brief phase of the orbit when the neutron star ventures close enough to its companion to accrete a clump of material or interact with its stellar wind, triggering a brief period of radio emission. This would make the event not a solo performance but a duet, with the timing dictated by the strict rules of orbital mechanics. the enduring enigma of GCRTJ 1745-3009 lies in its frustrating combination of clarity and mystery. It gave us a clear, measurable period, a solid clue that most mysterious transients refuse to provide, yet it vanished before we could gather enough data to pinpoint its exact nature. It remains a single, perfect data point in the vast ledger of cosmic anomalies, a ghost that sang a brief, rhythmic song from the galaxy's crowded core and then fell silent, leaving us with a beautiful set of theories and the lingering hope that somewhere another cosmic heartbeat is waiting to be heard. While our search often focuses on fleeting bursts or deliberate beacons, some of the most profound cosmic signals are not brief events at all, but vast, lingering glows that paint a new picture of the space around us. This brings us to a discovery that fundamentally rewrote our understanding of one of our closest stellar neighbors, the Geminga pulsar. Located just about 800 light-years away in the constellation Gemini, Geminga has been a familiar object since its discovery in the 1970s. It's a quiet, middle-aged pulsar, the dense, spinning remnant of a supernova that exploded over 300,000 years ago. For decades, we studied its regular radio pulses and its faint visible light, thinking we knew this nearby stellar corpse fairly well. That was until the High-Altitude Water Cherenkov Observatory, or HAWK, turned its gaze toward it and revealed something astonishing. Geminga is not just a point of light. It is surrounded by a colossal, faint halo of extremely high-energy gamma rays, a shimmering sphere of tera-electronvolt photons that stretches for dozens of light-years in every direction. This TV halo was a complete surprise and a significant challenge to established astrophysical models. For a long time, scientists had theorized that pulsars like Geminga were the primary sources of mysterious cosmic rays, high-energy protons and atomic nuclei that constantly bombard Earth's atmosphere from all directions. The prevailing model was fairly straightforward. A pulsar's powerful magnetic field and rapid spin accelerate charged particles to nearly the speed of light, and these particles then shoot out into the galaxy like cosmic bullets, eventually reaching us as cosmic rays. The discovery of the TV halo around Geminga showed that this process is far more complex and inefficient than we ever imagined. The halo itself is the telltale sign. Those high-energy gamma rays are not coming from the pulsar directly. They are created when the accelerated particles, the very cosmic rays we were looking for, get trapped in a turbulent cloud of magnetic fields and gas surrounding the pulsar. Before these particles can escape into the wider galaxy, they collide with photons of starlight or particles within this local cloud, and these collisions produce the gamma-ray glow that HAWK detected. The sheer size of the halo sent a clear message. Geminga's ability to inject its accelerated particles into interstellar space is severely hampered. The particles are getting bogged down, stuck swirling around in the pulsar's backyard for tens of thousands of years before they can break free and journey across the galaxy. This means that for a nearby, well-studied pulsar like Geminga, the number of cosmic rays that actually make it to Earth is far lower than our models predicted. It forces a major rethink of our galactic cosmic ray budget. If other pulsars are similarly inefficient, surrounded by their own invisible halos that act like cosmic containment fields, then we must look for other, even more powerful and exotic sources to explain the torrent of high-energy particles that continually rain down on our planet. This one faint, extended glow has become a powerful signal in its own right, a silent testament to the complex and often hidden physics that governs how energy is transferred and contained within the ecosystems of our galaxy. It reminds us that sometimes the most important discoveries are not the bright, flashing points of light, but the subtle, vast structures that connect them, revealing a universe far more intricate and interconnected than we ever dreamed. For all the awe-inspiring power and mystery of fast radio bursts, one of their most profound contributions to science may have nothing to do with their origins at all, but with the incredible journey they take to reach us. These titanic flashes are more than just cosmic enigmas. They are the universe's ultimate intergalactic probes, illuminating the darkest, emptiest voids between galaxies and helping to solve one of cosmology's most persistent puzzles, the case of the missing baryons. Baryons are the particles that make up the ordinary matter we're all familiar with, the protons and neutrons that constitute stars, planets, and indeed our own bodies. For decades, astronomers have been able to make a very precise inventory of all the baryons that existed in the very early universe by studying the cosmic microwave background. They can also count the baryons that are locked up in stars and galaxies in the more recent universe, but when they compare these two ledgers, a huge discrepancy emerges. Nearly half of all the ordinary matter that should be present in the modern universe seems to have simply vanished. It's as if you had a detailed packing list for a massive shipment, but when you opened the box, half the items were gone. This was the missing baryon problem, a baffling gap in our understanding of the cosmos's contents. The leading theory proposed that this missing matter wasn't truly missing, it was just hiding in plain sight, or rather in the dark. Scientists suspected it was spread out in a vast, diffuse web of incredibly hot, incredibly thin gas that fills the space between galaxies. This is the warm-hot intergalactic medium, or WIM. Imagine a ghostly, superheated fog, so tenuous that it might only contain a few dozen particles per cubic meter, a vacuum far emptier than anything we can create in labs on Earth. This gas is too hot to see in visible light and too diffuse to emit significant X-rays on its own, making it virtually invisible to our telescopes. For years, it remained a theoretical idea, a ghost in the cosmic machine that was nearly impossible to confirm. This is where fast radio bursts, especially those from billions of light years away, become the perfect tool for the job. Their secret lies in that same dispersion measure we've discussed before, the delay of lower frequency radio waves compared to higher ones. This delay isn't a flaw, it's a feature. It's a direct measurement of the total number of free electrons the radio burst encountered on its multi-billion light-year journey to Earth. Since these free electrons are found in ionized gas, and ionized gas is made of baryons, the dispersion measure is essentially a cosmic scale. Each FRB allows astronomers to weigh all the ionized material between its source and us. By carefully analyzing the dispersion measures from a large number of FRBs at different distances, astronomers can begin to build a map. They can calculate the average density of free electrons along these immense lines of sight and compare it to the density they would expect if all the predicted baryons were indeed floating in the intergalactic medium. The results have been nothing short of a breakthrough. The collective data from these diffuse FRBs has provided the first solid, observational evidence for the WIM. The numbers are adding up. The missing baryons have been found. They were never missing, they were just hiding in the most immense and empty regions of space, and it took the most powerful and fleeting flashes in the universe to finally light them up for us to see. This turns our perspective on its head. An FRB is no longer just a mysterious event to be explained. It is also a brilliant flashlight beam shot across the cosmos, revealing the invisible architecture of the universe itself. Every time one of these bursts is detected, it doesn't just tell us about the violent physics at its source. It also conducts a census of every electron it passed on its way. In this way, the greatest mysteries often become our greatest tools, and in helping us find what was lost, fast radio bursts have secured their place as one of the most valuable phenomena in modern astronomy. But just as dispersion gives us a cosmic scale to weigh the universe, another property of these radio waves offers a forensic tool to dissect the very environment that birthed them. This brings us to the remarkable story of FRB 110523, a signal that didn't just travel through space, it carried with it a detailed fingerprint of the powerful magnetic fields it had struggled through, a phenomenon known as the Stroop effect for the cosmos. Discovered in archival data from the Green Bank telescope, This particular burst was special not for its power or its distance, but for what happened to its polarization as it journeyed toward us. Light, including radio waves, can be polarized, meaning its waves oscillate in a preferred direction. As this polarized light travels through a magnetized plasma, its direction of polarization can slowly rotate, a process known as Faraday rotation. The degree of this rotation is called the rotation measure, and it is a direct probe of the strength of the magnetic field and the density of the electrons it encountered along the line of sight. FRB 110523 presented astronomers with a rotation measure of staggering proportions. It was one of the highest ever recorded for an extragalactic source, indicating that this burst had fought its way through an exceptionally strong and complex magnetic environment. Think of it like this. Imagine a beam of light is a message written on a piece of paper. A weak magnetic field might slightly smudge the ink, but the field this FRB passed through was so powerful it was as if the entire message had been put through a paper shredder and then meticulously taped back together in a completely different order. The incredible rotation measure was the telltale clue that the source of this burst was embedded in a cosmic maelstrom, a place of unimaginable magnetic violence. This single measurement acted like a cosmic coroner's report, allowing scientists to rule out entire categories of possible origins and point a finger at a very specific crime scene. The most likely environment capable of generating such an extreme Faraday rotation is the turbulent magnetized nebula of a recent supernova remnant. This strongly supports the theory that this FRB was produced by a very young magnetar, perhaps only a few decades old, still swaddled in the hot, dense, and ferociously magnetic shell of expanding debris from the star that gave it birth. In this scenario, the radio burst is the scream of the newborn magnetar, and the extreme rotation measure is the unmistakable signature of the chaotic nursery it still calls home. An alternative, though less likely, possibility is that the burst originated perilously close to the supermassive black hole at the center of its host galaxy. The intense gravitational forces and swirling accretion disks around such monsters can also generate magnetic fields of unbelievable strength, which could have imprinted this unique signature on the passing radio waves. The Stroop signal, through its polarized fingerprint, demonstrates that FRBs are more than just simple flashes. They are complex messages encoded with information about their entire journey. By learning to read this subtle twisting of light, we gain the ability to peer into the heart of the most extreme environments in the universe, places we could never hope to visit directly. It transforms each detection from a mere point of light into a detailed diagnostic tool, allowing us to conduct remote astrophysical surgery on some of the most energetic and mysterious objects in the cosmos. Yet for all the power of FRBs to illuminate the vast intergalactic voids, some of the most subtle and precise signals we study come not from explosive events, but from the steady, clock-like ticking of the most distant objects in the universe. This brings us to the immensely powerful technique of very long baseline interferometry, or VLBI, and the peculiar ghost signals that occasionally haunt its pristine data. VLBI is arguably one of the most breathtaking achievements in all of astronomy. By synchronizing radio telescopes scattered across the globe, or even in space, and combining their data, astronomers can effectively create a virtual telescope the size of the entire Earth. This provides a resolution so incredibly sharp it could, in theory, allow you to read a newspaper on the surface of the moon from your backyard. The workhorse targets for these ultra-precise observations are quasars, the intensely bright cores of distant galaxies powered by supermassive black holes feasting on surrounding matter. Because these cosmic beacons are so phenomenally far away, they appear fixed in the sky, providing what seems to be a perfect, immovable grid of reference points against which we can measure everything else. This quasar grid is not just for astronomy, it is the foundation for our most advanced celestial navigation systems. Satellites and deep space probes use the precise timing of radio waves from these quasars to determine their position in space with centimeter-level accuracy. The entire process relies on an assumption of perfect regularity. The arrival time of a quasar's signal at each telescope in the global network is predicted with exquisite precision based on the known location of the quasar, the precise positions of the telescopes on Earth's rotating surface, and the calculated delay as the signal passes through Earth's atmosphere. The entire system is a symphony of exact timing, where a discrepancy of even a few billionths of a second is a significant event that must be explained. And sometimes explanations are hard to find. These discrepancies are the ghost signals, tiny, unexplained timing glitches that appear in the data. The vast majority are quickly traced to a host of mundane terrestrial culprits. A tiny instrumental drift in one of the telescope's atomic clocks, the most precise timekeeping devices ever built, can introduce a minuscule error. A passing weather front with its shifting pockets of humid air can slightly slow down the radio waves, altering their arrival time. The most common and persistent villain is our own planet's ionosphere, a layer of the upper atmosphere filled with free electrons. The density of this plasma is constantly shifting due to solar activity, and like a funhouse mirror, it can bend and delay radio waves in complex, dynamic ways that are difficult to model perfectly. Even the relentless drift of tectonic plates, slowly moving the telescopes themselves by minuscule amounts, must be accounted for. The process of VLBI is a constant battle to identify and subtract these countless sources of noise. But what happens when a timing anomaly refuses to be explained? When every known instrumental and atmospheric effect has been ruled out and a glitch remains, sitting in the data like a single wrong note in an otherwise flawless performance. It is in these rare moments that scientists allow themselves to consider more exotic possibilities. Could the path of the radio wave have been perturbed by something truly unseen? One speculative theory points to clumps of dark matter. If dark matter is made of actions or other exotic ultralight particles, it might not be perfectly smoothly distributed. It could form subtle, diffuse clumps drifting through the galaxy. As a radio wave from a distant quasar passes through one of these hypothetical clumps, the interaction with this strange form of matter could, in theory, cause a slight shift in the wave's properties, manifesting as a tiny, anomalous timing delay. Another idea involves primitive black holes, small and ancient relics from the Big Bang, drifting unseen through space. The gravitational field of such an object passing near the line of sight could briefly warp spacetime, acting as a temporary gravitational lens and delaying the signal in a way that mimics a timing glitch. These exotic explanations remain firmly in the realm of fascinating speculation. The last resort after every earthly cause has been exhaustively eliminated. The ghosts in the VLBI data are almost certainly phantoms of our own, making a testament to the incredible difficulty of achieving perfection in measurement. Yet their very existence is a powerful symbol of scientific rigor. They represent the unwavering commitment to questioning every anomaly, no matter how small, because history has shown us that sometimes the slightest whisper in the data can be the first hint of a truth that reshapes our understanding of the cosmos. Just as we train our most powerful telescopes on the depths of space, the universe occasionally sends a mystery right through our front door, a visitor from the vast interstellar void that challenges our very definitions of what is natural. This brings us to a story that captivated the world in 2017, not of a signal from the stars, but of a silent, speeding object, the first known interstellar visitor, given the Hawaiian name Oumuamua, meaning scout. Its arrival was as dramatic as it was historic. Sped through our solar system at breathtaking velocity, its hyperbolic orbit, a path too fast to be bound by the sun's gravity, declared its origin loud and clear. This was a traveler from another star. But it was its bizarre physical properties that truly ignited a firestorm of scientific debate and public fascination. observations revealed an object unlike any asteroid or comet we had ever seen. It was wildly elongated, perhaps 10 times as long as it was wide, tumbling end over end through space. Most puzzling of all, as it departed the inner solar system, it exhibited a tiny but undeniable non-gravitational acceleration. It wasn't just falling under the influence of the sun's gravity. Something was giving it an extra subtle push. The immediate and thrilling question was, what could that something be? For comets within our solar system, such an acceleration is common and is caused by outgassing the sun's heat, vaporizing ices on the surface, creating a jet of material that acts like a natural rocket engine. But exhaustive searches by the world's best telescopes could find no evidence of the classic signature of outgassing, no coma of gas and dust, no tail streaming behind it. Oumuamua was accelerating in utter silence with no visible mechanism. This profound anomaly opened the door to a host of exotic explanations, and it was Harvard astronomer Avi Loeb who most famously and provocatively advanced the possibility that we might be looking at a piece of alien technology. His hypothesis was that the object's strange acceleration could be explained by radiation pressure from sunlight itself. If Oumuamua were an extremely thin, lightweight structure, a solar sail, perhaps a derelict one from a distant civilization, then the photons from the sun could be pushing on it just enough to account for its mysterious motion, all without any need for visible outgassing. This extraordinary idea, while considered highly speculative by most of the scientific community, was nevertheless deemed worthy of investigation by the Breakthrough Listen initiative. If there was even a minuscule chance that this was an artificial object, it was a scientific imperative to listen. Just weeks after its discovery, the massive 100-meter Green Bank telescope in West Virginia was tasked with a critical mission: to point its immense dish at the rapidly receding Oumuamua and listen for any sign of an artificial radio transmission. The logic was clear. If this object were indeed a piece of technology, whether a functioning probe, a communication buoy, or a discarded light sail, it might still be emitting some form of radio frequency leakage or even a deliberate beacon. The team scanned across 4 radio bands from 1 to 12 gigahertz, covering a vast range of frequencies that could carry everything from simple carrier waves to complex data streams. For a total of 6 hours, they collected data, listening for any signal that stood out from the background cosmic static. The result, after meticulous analysis, was a profound and definitive silence. No narrowband signals were detected, no broadband emissions that would indicate technology. The object was as radio quiet as a natural rock tumbling through the void. This null result did not and could not completely disprove the light sail hypothesis. A derelict, dead piece of machinery would, of course, be silent. But in the careful calculus of science, the absence of evidence is a form of evidence itself. It shifted the weight of probability away from the extraordinary and back toward the natural, forcing researchers to double down on finding a natural explanation that could account for all of Oumuamua's oddities without requiring a rewrite of astrophysics. And indeed, a compelling natural theory soon emerged, one that is now widely accepted within the astronomical community: the nitrogen iceberg model. This theory proposes that Oumuamua was not a solid rock, but a fragment of solid nitrogen that was chipped off the surface of a Pluto-like exoplanet in a distant solar system millions of years ago. As this nitrogen iceberg approached our sun, the heat would have caused the frozen nitrogen on its surface to sublimate, turn directly from a solid into a gas. Because nitrogen ice is very neutral and wouldn't produce the dusty, reflective coma of a water ice comet, this outgassing could have been virtually invisible to our telescopes, yet still provided enough of a jet-like thrust to explain the non-gravitational acceleration. The object's elongated shape could simply be a result of the way such a fragile icy body erodes over its long journey. The story of Oumuamua, from its discovery to the targeted search for signals, is a perfect case study in how modern science navigates the line between boundless curiosity and rigorous skepticism. It demonstrates our willingness to chase even the most thrilling possibilities while ultimately allowing the evidence, or the lack thereof, to guide us toward the most plausible truth. It reminds us that the universe is capable of producing natural wonders strange enough to mimic our wildest science fiction, and that the search for answers, whether they point to nature or beyond, is a journey that requires both an open mind and a critical eye. Yet even as we study the silent, icy visitors from other stars, our history is filled with moments where a signal from a nearby sun seemed to shout with possibility, only to reveal a far more terrestrial origin. This was the case with one of the most perplexing signals of the modern SETI era, a bizarre transmission that seemed to emanate from one of our closest stellar neighbors. In the spring of 2017, scientists at the Arecibo Observatory in Puerto Rico were conducting a routine campaign, observing a series of red dwarf stars. These small, cool stars are among the most common in the galaxy, and their planetary systems are prime targets in the search for habitable worlds. On May 12th, their focus was Ross 128, a quiet red dwarf star just 11 light-years from Earth. For 10 minutes, the massive dish listened, and then the data was recorded and stored. It wasn't until weeks later, when astronomers Abel Mendes and his team were reviewing the observations, that they found something that made them do a double take. There it was, a signal that was, in Mendes's own words, very peculiar. This was no ordinary blip of cosmic static. The signal was detected at around 4 to 5 gigahertz, and it possessed a combination of characteristics that made it instantly intriguing. First, it was deeply modulated, meaning its strength rose and fell in a series of slow, drifting pulses. This created a wide-band, quasi-periodic structure that was completely unlike the narrow-band, steady tone expected from a simple beacon. It was a complex, almost shimmering signal, and it appeared to be dispersed, a key signature of an interstellar origin, as if it had traveled through the tenuous plasma of deep space to reach us. The fact that it was seen only in the direction of Ross 128 and not in the empty patches of sky observed immediately before and after made the case for a genuine extraterrestrial transmission seem surprisingly strong. For a brief, electrifying moment, the team at Arecibo had to confront the staggering possibility that they might have detected something real. What followed was a masterclass in scientific rigor and public transparency. Rather than announce a discovery, the team did the exact opposite. They published their findings online and openly asked for help from the broader astronomical community. This was not a search for glory, it was a collaborative hunt for the truth. The immediate goal was to listen again. In a coordinated effort, the Green Bank Telescope in West Virginia and the Allen Telescope Array in California both pointed their dishes at Ross 128, hoping to catch a repeat performance of the strange signal. Simultaneously, a team at the SETI Institute's Buckwheat Optical Observatory in Panama began optical observations, looking for any potential laser pulses that might be associated with the radio transmission. The world watched and waited, the air thick with a potent mix of excitement and skepticism. The follow-up observations were crucial, and their result was definitive: silence. The signal did not repeat. This single fact was a massive blow to the extraterrestrial hypothesis. A deliberate, intelligent beacon would almost certainly be persistent or regularly repeating, not a one-off event. With the alien possibility rapidly fading, the investigation turned forensically toward Earth. The team began an exhaustive process of elimination, analyzing every possible source of human-made radio frequency interference. They considered aircraft, satellites, ground-based radar, and even other astronomical instruments. The breakthrough came when they realized that the signal's peculiar characteristics, its wide-band nature and its slow, drifting modulation, were a perfect match for the transmissions from geostationary satellites. These satellites orbit at an altitude of 35,786 kilometers, fixed relative to a point on Earth's equator. From the perspective of the moving Arecibo dish, which must track the rotation of the Earth to stay fixed on a star, a signal from a geostationary satellite would appear to drift slowly through the telescope's field of view, creating exactly the kind of quasi-periodic, modulated signature they had observed. The final, conclusive piece of evidence was that multiple geostationary satellites were known to be operating in the exact frequency band where the signal was detected. The Ross 128 signal, once a thrilling mystery, was officially closed as a case of mistaken identity. It was not a message from a distant civilization, but an echo of our own technological presence, a ghost created by our own satellites reflecting signals meant for television or phone calls. Yet its story is far from a failure. It stands as a powerful testament to the integrity of the modern SETI process. It demonstrated a commitment to transparency and collaboration, a willingness to openly share puzzling data with the global community to find an answer. It highlighted the incredible and growing challenge of conducting radio astronomy from a planet that is now enveloped in a shell of its own artificial transmissions. Most importantly, it proved that the scientific method works. The initial excitement was responsibly channeled into a meticulous, evidence-based investigation that followed the clues to their logical, earthly conclusion. The Ross 128 event wasn't a disappointment. It was a successful drill, a fire alarm that tested our systems and proved that when, or if, the real signal ever comes, we will be ready to identify it with confidence, having learned to recognize the sophisticated illusions our own world can create. Just when we thought the universe had exhausted its capacity for surprise, it delivered a gift-wrapped enigma during the holiday season. A cosmic event so strange and so long-lasting it would take years of detective work to even begin to understand its origins. This is the story of the Christmas burst, officially catalogued as GRB 10125A, detected by NASA, a Swift satellite on December 25, 2010. This was no ordinary flash in the gamma-ray sky. While most gamma-ray bursts, the universe's most powerful explosions, are over in a matter of seconds or minutes, the Christmas burst kept going for a baffling 28 minutes. It wasn't just its marathon duration that made it a puzzle. It was the bizarre and conflicting story told by the light it emitted across the entire electromagnetic spectrum. This event became a classic case of how different astronomical messengers can sometimes tell a story that seems to contradict itself, forcing scientists to become cosmic interpreters to find the truth hidden within the dissonance. The initial gamma-ray signal was bizarre enough, but the real mystery unfolded in the afterglow. As Swift automatically slewed to point its X-ray and ultraviolet/optical telescopes at the source, it revealed a light curve that defied all established categories. The optical light began to fade in a way that was initially consistent with a typical long-duration GRB, which is usually associated with the death of a massive star in a supernova. But then, something strange happened. After about a week, the optical light stopped fading and instead held steady at a constant brightness for an astonishingly long time before finally beginning a very slow decline. This was utterly unprecedented. A typical supernova-powered GRB afterglow shows a smooth, continuous fade. This plateau, this stubborn refusal to dim, suggested an energy source was continually pumping energy into the system, re-energizing the fading embers long after the initial explosion should have been over. Astronomers were presented with a cosmic riddle, and the theories they developed to solve it were as creative as they were divergent. One of the most imaginative and delightful early hypotheses was literally a Christmas-themed catastrophe. Could this incredibly long burst have been caused by a massive comet-like object, perhaps a celestial snowball several kilometers across, falling onto the surface of a neutron star? In this scenario, the prolonged gamma-ray emission would be the result of the comet's material being shredded and consumed by the neutron star's immense gravity over the course of half an hour. The subsequent optical afterglow could then be explained by the debris from this cataclysmic feast settling into a disk around the star and slowly radiating its energy away. It was a wonderfully festive idea, a cosmic version of throwing a giant Yule log on the fire, but it was ultimately deemed too exotic and unlikely to explain the sheer scale of the energy involved. A second, more robust theory emerged, suggesting we were witnessing a very special kind of supernova from a great distance. Perhaps a massive star had collapsed not directly into a black hole, but into a highly magnetic neutron star, a magnetar. The birth of this magnetar, with its unbelievably powerful magnetic field, could provide the long-lasting central engine needed to explain both the extended gamma-ray emission and the peculiar plateau in the optical light. The magnetar's furious spin and decaying magnetic field would inject energy into the expanding supernova shockwave for weeks or months, acting like a battery that kept the entire system glowing far longer than a simple one-time explosion could. This was a solid, respectable theory that fit many of the observed facts, but it still felt like trying to force a square peg into a round hole. The light curve was just a little too weird, a little too unique. The breakthrough in solving this multi-messenger mystery came from a crucial piece of evidence that had been missing: a precise distance. Early observations struggled to pin down exactly how far away the Christmas burst was, and distance is everything in astronomy because it dictates the true energy of an event. The initial assumption, based on the light curve's shape, was that it was a typical GRB billions of light years away. But years later, painstaking analysis using the Hubble Space Telescope and large ground-based observatories finally managed to secure a spectroscopic redshift. The result was shocking. GRB 10125 was not in a distant galaxy. It was located right here in our own cosmic neighborhood, a mere 2.5 billion light-years away, which is practically next door for events of this scale. This new distance measurement changed everything. The energy budget for the burst was now far smaller than originally thought. It wasn't an impossibly energetic supernova, it was something else entirely. This crucial distance data allowed the leading theory to finally snap into focus. The most likely explanation is that we witnessed a spectacularly violent stellar merger. Imagine a binary system where a neutron star is locked in a close, deadly dance with a helium star, the exposed, helium-rich core of a star that has already shed its outer hydrogen layers. Over time, their orbits decay, and the neutron star begins to spiral inward, eventually plunging into the core of its helium companion. This merger triggers a colossal explosion, not a standard supernova, but a unique thermonuclear detonation that shreds the helium star apart. The incredibly long gamma-ray burst is the signature of the neutron star's final death spiral and the immediate aftermath of the merger. The strange, plateauing optical afterglow is then the light from the expanding debris of the destroyed helium star, heated by the radioactive decay of heavy elements forged in the incredible heat and pressure of the explosion. This model, a rare helium star-neutron star merger, elegantly explains every perplexing feature of the Christmas burst. It accounts for the duration, the energy, and most importantly, the multi-wavelength story that seemed so confusing at first. The different messengers weren't contradicting each other. They were each telling a different chapter of the same violent, beautiful, and incredibly rare story of stellar death and transformation. While the intense drama of gamma-ray bursts and stellar mergers unfolds across the cosmos, a far more subtle and profound hunt was taking place, one that sought to uncover the very nature of the universe's most elusive ingredient, dark matter. This brings us to a signal that wasn't about a violent explosion, but a faint, specific whisper from a known object that, for a moment, seemed to speak of something entirely new. Our focus shifts to the pulsar wind nebula known as 3C58, the remnant of a supernova observed by Chinese and Japanese astronomers in the year 1181. Within this beautiful, turbulent cloud of expanding debris lies a rapidly spinning neutron star, and it was here that a team of researchers believed they had found a clue to one of physics' greatest mysteries. The theory they were testing is as elegant as it is revolutionary. It involves a leading hypothetical candidate for dark matter, a particle called the action. These particles are thought to be incredibly light and abundant, flowing through the universe in a vast, unseen ocean. The key idea is that in the presence of an immensely powerful magnetic field, like the one generated by a neutron star, these actions could spontaneously convert into photons, particles of light. This conversion would produce a very specific telltale signature, a faint but persistent excess of radio waves, and crucially, this radio emission would be concentrated at a very specific frequency that is directly tied to the mass of the action particle itself. It would be a direct, detectable signal of dark matter transforming into something we can see. When researchers pointed radio telescopes at 3C58, they reported exactly that, a faint, narrow radio excess at a specific frequency that didn't seem to have a clear, conventional astrophysical explanation. The excitement was palpable. This wasn't an indirect gravitational inference of dark matter. This was a potential direct detection of the particle itself, a signal generated by its very transformation into ordinary light. It suggested that we might not need massive underground detectors to find dark matter. We might simply need to listen to the right neutron star with a sensitive enough radio ear. The implications were staggering, pointing toward a future where we could finally identify the substance that makes up 85% of the matter in the universe. However, the scientific community, driven by a necessary and healthy skepticism, responded not with celebration but with intense scrutiny. Extraordinary claims require extraordinary evidence, and the evidence for actions at 3C58 was exceptionally subtle, sitting right at the edge of detectability. Other teams of astrophysicists began to dig into the data, and they quickly proposed a host of alternative, mundane explanations that could perfectly account for the observed signal without requiring any new physics. The primary counter-argument was that the radio excess could be easily explained by a slightly more complex model of the nebula's own synchrotron radiation. Synchrotron radiation is the well-understood process by which electrons, spiraling at near light speed along magnetic field lines, emit light across the electromagnetic spectrum. In a complex environment like 3C58, the distribution of these electrons isn't perfectly smooth. There could be clumps or slight variations in energy that would naturally produce small bumps and wiggles in the overall radio spectrum. The proposed action signal, critics argued, was simply one of these wiggles, a perfectly natural feature that only looked unusual if you assumed an overly simplistic model for how the nebula's emission should behave. There was no need to invoke a hypothetical particle from the dark sector when standard astrophysics, with all its known complexities, could do the job. This back and forth between claim and critique is not a failure of science, it is the very engine of discovery. The case of the 3C58 signal perfectly highlights the immense challenge of claiming a dark matter detection, especially when searching for it against the incredibly bright and complex backdrop of known astrophysical phenomena. It underscores a critical lesson: the universe is messy, and its natural processes can create illusions that perfectly mimic the signals we desperately hope to find. This event forced theorists to refine their models and experimentalists to develop even more rigorous methods for distinguishing a true action signal from astrophysical background noise. While the initial excitement may have faded, the investigation it sparked continues to drive the field forward, teaching us to be ever more careful, ever more precise, and ever more awestruck by the universe's ability to hide its deepest secrets in plain sight. While the universe often presents us with signals that are bright across multiple wavelengths, Some of its most puzzling messages are those that appear in only one specific slice of the electromagnetic spectrum, like a lone instrument playing in an otherwise silent orchestra. These are the uncorrelated sources, enigmatic objects that blaze brightly in radio waves but show absolutely nothing in X-rays or vice versa, defying our fundamental models of how cosmic engines are supposed to work. Imagine pointing a radio telescope at a patch of sky and finding a brilliant point-like source, a beacon of intense radio emission. You then immediately swing the world's most powerful X-ray and optical telescopes toward that exact same spot, expecting to see the high-energy fury and visible light you'd anticipate from such a powerful object, only to be met with nothing but empty blackness. The radio source is an orphan, a cosmic soloist with no accompanying band, and its solitary performance challenges everything we think we know. This disconnect strikes at the heart of our understanding of active galactic nuclei and microquasars. Our unified models for these objects are built on the idea of a central engine, a supermassive or stellar mass black hole, surrounded by a swirling accretion disk of superheated material. In this model, we expect to see a coordinated symphony of light, X-rays from the searingly hot inner disk close to the black hole, optical and ultraviolet light from the outer disk, and powerful radio jets shooting out from the poles, beaming energy across space. The relative brightness of each part of this symphony depends on our viewing angle. If we look directly down the jet, a phenomenon known as blazar orientation, the relativistic beaming effect can make the radio emission appear tremendously amplified, while the disk itself might be hidden from view. This is one of the leading explanations for these uncorrelated sources. We might be seeing a system where our viewpoint is perfectly aligned to see the brilliant jet in radio, but the accretion disk and its X-ray output are either obscured by thick dust or simply not pointed in our direction. But beaming effects can't explain every orphaned signal. Another compelling possibility is that we are witnessing an object shrouded in the most extreme levels of obscuration imaginable. Picture a nascent supermassive black hole or a microquasar are still buried deep within its cosmic cradle, a dense cocoon of gas and dust so thick that even high-energy X-rays cannot penetrate it. The radio waves, with their longer wavelengths, might be the only form of energy capable of escaping this dense shroud, trickling out to reach our telescopes while all other light is trapped within. We would see a bright radio source completely unaware of the violent X-ray prison raging at its heart. Alternatively, we could be catching a transient event in its very earliest or latest stages. A tidal disruption event where a star is shredded by a black hole might first produce a flash of radio waves as the initial debris is ejected, with the X-ray emission from the accretion disk taking days or weeks to ramp up. If our telescopes weren't looking at the right moment, we might only catch one part of this evolving sequence, leaving us with a single, confusing piece of a much larger puzzle. The most thrilling possibility, however, is that these uncorrelated sources represent something entirely new, transient phenomena that we have not yet categorized, events that only produce significant emission in a very narrow band of light. Perhaps they are signatures of exotic magnetic reconnection events on a scale we can scarcely imagine, or the birth cries of previously theoretical objects like magnetospheric eternally collapsing objects. Each orphaned signal is a direct challenge to our hubris, a reminder that our models are built on the objects we have already found, and that the universe is under no obligation to limit its creativity to our current understanding. They force astronomers to become detectives, using the absence of evidence as a form of evidence itself, and driving the development of new, multi-messenger observation strategies that can finally bring the entire cosmic orchestra into tune. Yet, even as the Geminga pulsar's immense, faint halo of tera-electronvolt gamma rays revealed the secrets of trapped cosmic rays, this familiar stellar corpse had another, even more energetic surprise in store, a mystery radiating from its very core. While the Hawk Observatory was mapping the vast, faint glow of the TV halo, NASA's Fermi Gamma Ray Space Telescope was focusing on a different energy range, scrutinizing the pulsar itself at giga-electronvolt or GeV energies. And there, nestled in the immediate vicinity of the pulsar, Fermi detected something that didn't quite fit: a significant and puzzling excess of gamma-ray emission. This wasn't the smooth, extended halo seen at higher energies. This was a more concentrated, intense glow right at the heart of the system, a signal that sparked a lively and ongoing debate about what powerful processes were at work in Geminga's energetic engine. The leading and most widely accepted explanation points to the incredible physics of the pulsar wind nebula itself, the magnetized cloud of particles that surrounds the rapidly spinning neutron star. Geminga is a powerhouse, generating a furious wind of electrons and positrons that are accelerated to nearly the speed of light by its powerful magnetic fields and rapid rotation. As these ultra-relativistic particles tear through the nebula, they inevitably collide with lower-energy photons, including the abundant light from the cosmic microwave background radiation that fills all of space. In these high-speed collisions, the photons get a massive energy boost, a process known as inverse Compton scattering. It's like a ping-pong ball being smashed by a professional player. The photon is sent flying with tremendously increased energy, becoming a gamma ray in the GeV range. This elegant and well-understood astrophysical process can beautifully account for the excess emission, painting a picture of a natural and violent particle accelerator operating right on our cosmic doorstep. However, the sheer intensity and specific characteristics of this GeV excess were so pronounced that they prompted a more speculative and far more thrilling alternative hypothesis. Could this be the long-sought signature of dark matter annihilation? The theory proposes that dark matter, the invisible glue that holds galaxies together, might be made of weakly interacting massive particles or WIMP. If this is true, then in regions where dark matter is exceptionally dense, these particles could occasionally collide and annihilate each other, converting their mass directly into energy and producing a cascade of particles, including gamma rays at specific energies. A nearby, dense object like a pulsar could potentially be surrounded by a concentrated clump or spike of dark matter, drawn in by its powerful gravity over millions of years. The gamma-ray excess from Geminga in this scenario would be the radiant signature of these phantom particles meeting their end, a faint but detectable glow from the universe's most elusive substance. This debate between the astrophysical and the exotic is a perfect example of the scientific process at its best, where a single observation can ignite a firestorm of creative theorizing. Proponents of the dark matter interpretation must carefully model the expected emission spectrum from WIMP annihilation and see if it matches the unique energy signature observed by Fermi. Meanwhile, astrophysicists work to create increasingly sophisticated models of the pulsar wind nebula, striving to see if inverse Compton scattering alone can replicate every nuance of the data. The investigation is incredibly challenging because the two hypotheses are not mutually exclusive. Both processes could be contributing to the signal, forcing researchers to untangle their individual impacts. The case of the Geminga GeV excess demonstrates a profound truth in modern astronomy, that even a well-known, seemingly familiar object can suddenly reveal a new layer of mystery, pushing the very boundaries of our understanding. It shows that the frontier of discovery isn't always about finding new, distant objects. Sometimes it's about looking at an old neighbor with new eyes and sharper instruments, asking deeper questions that challenge our most fundamental models of physics. Whether the excess is ultimately confirmed as a natural particle accelerator or as a groundbreaking glimpse of dark matter, its very existence pushes our models to their limits, ensuring that this nearby pulsar will remain a source of intense scrutiny and captivating mystery for years to come. Just when we think we have the universe neatly categorized, a discovery emerges from the dimmest, coldest objects in the cosmos, forcing us to completely rethink what we know about magnetic fields and the very definition of a planet. Our journey now takes us to the strange and wonderful world of brown dwarfs, often called failed stars. These are cosmic in-betweeners, objects too massive to be considered planets, but not quite massive enough to ignite sustained hydrogen fusion in their cores and shine like true stars. They are cold, dark, and faint, slowly cooling over billions of years into planetary mass embers. For a long time, astronomers assumed they would be radio silent, their atmospheres too placid, and their energies too low to generate the kind of dramatic emissions we see from active stars. That assumption was spectacularly shattered with the detection of a powerful, structured, and highly polarized radio signal from a brown dwarf known as LSR J1835 plus 3259. This wasn't a random burst of static. It was a coherent, pulsating radio beacon that seemed completely out of place emanating from such a cold, faint object. The signal itself was a revelation. It was strongly polarized, meaning its radio waves were aligned in a specific, orderly fashion, a clear signature of a powerful and organized magnetic field at work. Even more astonishing was its periodicity. The signal pulsed with a remarkably stable rhythm. This level of structure and coherence is something we typically associate with two types of objects: man-made radio transmitters or the aural processes of a planet like Jupiter. The fact that this was coming from a brown dwarf sent theorists scrambling for an explanation. How could a cold, isolated ball of gas, barely larger than Jupiter, generate such a powerful and structured radio shout? The answer appears to lie in a fascinating cosmic dance, one that involves an unseen partner. The leading theory is that this brown dwarf is not alone. It may possess a large, orbiting planet or even a substantial moon. Just as Jupiter's volcanic moon Io drives its intense radio emissions, this hypothetical companion could be playing a crucial role. Here's how it likely works. The brown dwarf, despite its failure to become a star, still retains a surprisingly strong magnetic field. As an orbiting planet or moon moves through this magnetic field, it acts like a giant electrical generator, a process known as the unipolar inductor mechanism. This motion drives a tremendous current of charged particles along the magnetic field lines, which then flow down into the brown dwarf's atmosphere near its magnetic poles. When these accelerated particles slam into the atmospheric gases, they ignite a spectacular auroral display, just like the northern lights on Earth but on a planetary scale. It is this auroral process that generates the intense, coherent, and pulsed radio emission we detect. The stability of the pulse suggests the orbit of the driving body is very regular, turning the entire system into a kind of cosmic lighthouse with its beam sweeping through space with metronomic precision. This discovery fundamentally changes our understanding of these marginal objects. A brown dwarf is no longer just a cold, failed star. It can be a magnetically active world, capable of hosting its own complex planetary system and generating breathtaking light shows in its upper atmosphere. It blurs the line between planet and star, suggesting that the magnetic and auroral phenomena we see in our own solar system might be universal, occurring around countless faint objects throughout the galaxy. It also offers a thrilling new method for exoplanet detection. Instead of looking for the faint dimming of a star or the subtle wobble of its motion, we might now be able to simply listen for the powerful, pulsing radio beacon generated by a planet's interaction with its magnetic host, a ringing announcement of a hidden world's presence in the dark. Just when we thought the cosmic menagerie of radio transients was complete, with its millisecond pulsar ticks and explosive FRB shouts, astronomers have stumbled upon a new class of signal that operates on a timescale so languid it seems to defy the frantic energy of the universe. These are the ultra-long period radio transients, mysterious sources that switch on over minutes or even hours, shine for a while and then fade away like a cosmic lighthouse with an impossibly slow and deliberate rotation. Their behavior is nothing like the frantic, metronomic beats of pulsars or the split-second violence of fast radio bursts. This is a different kind of rhythm altogether, a deep, slow heartbeat echoing from a type of cosmic engine we are only beginning to imagine. The discovery of these objects sends a jolt through established astrophysics because their very existence challenges our understanding of rotational dynamics and magnetic braking. A pulsar's rapid spin is a result of the conservation of angular momentum. A massive star collapsing down to a city-sized object spins faster, just like an ice skater pulling in their arms. The magnetic fields of these neutron stars are so intense they act as brakes, steadily slowing the spin over millennia. For a neutron star to have a rotational period of several minutes or even hours, its magnetic field would have to be either extraordinarily weak, allowing it to keep spinning for eons, or unbelievably strong, acting as such an effective brake that it has slowed the star to a cosmic crawl. The latter possibility points directly to the most magnetic objects in the universe, magnetars. Could we be discovering a population of magnetars that are so old and so magnetically braked that they have spun down to these incredibly long periods? These would be the geriatric versions of the hyperactive magnetars we know, their furious youth long behind them, now ticking away with the slow, steady patience of a celestial grandfather clock. But magnetars are not the only possible culprit. Another compelling theory ventures into a different stellar retirement home: white dwarf binaries. White dwarfs are the Earth-sized embers left behind by stars like our Sun, and they can have strong magnetic fields in their own right. In a binary system where two white dwarfs orbit each other, their magnetic fields can interact in complex ways. As they spiral closer together, their magnetospheres can become connected, allowing currents to flow between them. This interaction can trigger periodic radio emission linked to their orbital period, which could easily be on the order of hours. Alternatively, an isolated, highly magnetic white dwarf spinning alone in the void could itself be the source. If its magnetic axis is misaligned with its rotation axis, it could beam radio waves toward us, but its much larger size and slower rotation would create these long, drawn-out pulses we are now detecting. The significance of these ultra-long-period transients is immense. They represent a clear and present gap in our knowledge, a whole new parameter space of celestial behavior that our current models didn't predict. Finding them is like a zoologist discovering that a well-explored forest is actually home to a species of mammal that only wakes up for one day every decade. Their slow, predictable nature is actually a gift to observers. It allows for detailed, real-time study of the entire emission cycle, from the gradual turn onto the peak of emission and the slow fade. This provides a wealth of data that can be used to probe the emission mechanisms and the environment around the source in a way that's impossible with a fleeting millisecond burst. These mysterious slow-beating hearts of the radio sky force us to confront the beautiful reality that our census of the cosmos is still wildly incomplete. They remind us that the universe is capable of inventing engines and rhythms far outside the confines of our current textbooks, operating on timescales that feel almost geological in their patience. Each new detection is not just another point on a map, but a fundamental question about the life cycles of stars, the limits of magnetic fields, and the incredible diversity of ways a celestial object can announce its presence in the silent, dark vastness of space. From the stark, singular shout of the wow, signal to the rhythmic, clockwork pulses of repeating fast radio bursts and the deeply puzzling GV excesses from objects like Geminga, our journey through 30 of the cosmos's greatest mysteries reveals a universe that is far noisier, more creative, and more mysterious than we ever dared to imagine. We have encountered signals that are chaotic and signals that are precise, whispers from our stellar neighborhood and titanic blasts from the edge of the observable void. pulses that last milliseconds and glows that persist for eons. Each one, from the tantalizing false alarms of BLC-1 and Ross 128 to the confirmed wonders of pulsars and magnetars, tells a story not just about the object that created it, but about our own relentless human drive to understand our place in this vast, dark ocean. What is perhaps most incredible is that behind every one of these enigmatic signals, whether ultimately explained by the violent physics of a neutron star or the subtle drift of a satellite, lies a monumental leap forward in our scientific capabilities. The pursuit of these cosmic ghosts has forced us to build bigger telescopes, develop sharper algorithms, and forge global collaborations that span continents. It has pushed the very limits of our imagination, compelling us to theorize about alien megastructures and dark matter particles, not as flights of fancy, but as serious scientific possibilities that must be rigorously tested and more often than not ruled out. This process of investigation, of passionate debate and meticulous verification, is the true engine of discovery. It is how we turn a squiggle on a chart into a fundamental new understanding of magnetic fields, stellar life cycles, and the very composition of the universe itself. And the most thrilling chapter in this story is yet to be written. The next generation of observatories, like the Square Kilometre Array, promises to be nothing short of revolutionary. With its unprecedented sensitivity and sheer scanning power, the SKA will listen to the cosmos with ears more attuned than any we have ever built. It will detect tens of thousands of new fast radio bursts, potentially pinpointing their origins with enough precision to finally identify their engines. It will scour the skies for technosignatures with a clarity that will make past false alarms a thing of antiquity, and it will probe the faintest radio glows with the power to unveil the secrets of dark matter and the missing baryons. We stand on the precipice of a new golden age of discovery, where the mysteries we've pondered for decades may finally yield their answers, only to be replaced by new, even more profound questions. The universe is not silent, it is a symphony of energy, and we are only just beginning to learn how to listen. Each signal is a piece of a grand cosmic puzzle, and the search for its meaning is one of the most inspiring adventures humanity has ever undertaken. Now we want to hear from you. After this journey through the unexplained, which of these galactic signals captured your imagination the most? Was it the haunting one-time mystery of the WOW signal, the predictable rhythm of FRB 1891-6, or the mind-bending possibilities of an object like Oumuamua? Share your thoughts in the comments below, and let's keep looking up.